hello. Hello, hello, hello. Hello, 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 hello.
Okay.
Yeah. Okay. So what I want to do today is, yeah, I did it. Shall I wait? Yeah. And how can we lift that? Thank you. Okay, guys, so today I want to first continue a little bit on what we, were discussing yesterday, and, understand a little bit more conceptually how, and also computationally, how do you calculate finite time Lyapunov exponents, how do you calculate, attractors and repellers. I'll show you a couple of slides. The code for computing the structures with all the README files and the instructions have been shared with you. I don't know if you looked at the GitHub repository that was shared, and this afternoon we're gonna have a tutorial, so we play a little bit with the codes. So today I want to spend a little bit more time on the conceptual part, and let's start with a mini recap of what we learned yesterday. So we basically derived these few equations. One was the Cauchy-Green strain tensor. Okay, and then we said, okay, let's denote by lambda max B, we called it no, actually lambda max, the largest eigenvalue of C, and then basically we define this FTLE finite time Lyapunov exponent. Can call it in a few ways as the logarithm of the square root lambda max t0 t of x0 divided by t minus t0. Let's put a norm where it's going to become clear why we put the norm there later. Okay. Okay, so if you just consider the little example we treated yesterday, was basically x dot equal to x, y dot equal to minus y plus x squared. What we did basically, we computed the flow map, then you compute the df, and now you can compute Cauchy-Green and the FTLE. Okay, and please do it, because if you do it, it's interesting that here you can compute all these quantities analytically. Usually the bottleneck for computing the Lyapunov exponent analytically is that you cannot really have an analytical expression of the trajectories. Okay, the rest is just trivial. You can always differentiate. C is just a multiplication, and the largest eigenvalue is just some polynomial of these basically entries of C. So this is the bottleneck of the time. Here you are lucky because we already have F. So here you can really compute this analytically. And have it as a function of initial condition. This is going to be a function of the time that you want to explore. I mean, remember, in this case, it's just one time because the system is time independent, okay? And the initial condition, okay? This is beautiful. You can play with analytically. You can also play with, plot the function. Okay. So I asked you yesterday to see what happens if the system is linear. If you start with a linear differential equation, who did it? Who tried? Yeah.
The Cauchy-Green tensor does not depend on the initial condition.
Beautiful. Yeah, it's a very powerful claim. Now we're going to do a quick explanation of why, and then we'll also understand the consequences. FTLEs for linear ordinary differential equation, or let's say velocity fields. Okay, so what is the most general form to write a linear differential equation, a vectorial differential equation, is this. You're gonna have basically some matrix that depends on time times x plus a vector. Okay, where x can be basically in Rn, because it could be any dimension, you know, n. And okay, b is a vector, p of t is also in Rn, and a is a matrix, a square matrix, n by n. Okay, so the general solution of this equation is of this form: x of t is equal to phi t0 t times x0 plus c of t. Okay, this is basically, if you want to understand this, is from the variation of constant formula, how to compute it. And this is basically, so you're going to have a matrix that is going to depend on time. Again, this you have to allow to depend on t0 and t, because the system is time dependent, so this differential equation is time dependent, or is non-autonomous. And what do you get from this equation? What do you get? You can compute immediately df what is the derivative of f, which is the trajectory. This is the same as f, if you will. Okay, this is the trajectory. When you differentiate the trajectory with respect to initial condition, what do you get? Phi. Good. So you really get this. It's just a matrix. It's going to depend on time, but it doesn't depend on initial condition. So this says that, you know, the formation gradients forgot where you started your journey with your trajectory. Okay, so this is independent of initial condition. This is very important. Okay, so in linear system, this means basically that in linear system, ODEs, and you know, if you want to have a more clear understanding of, you know, if someone gives you a velocity field, how do you understand if it's linear in space? We are talking about linear in space. I mean, yeah, it's not an easy question, right? Because you just get a data set, but you know, that means basically that there are not basically big spatial variations of this system in space, of these velocities in space. They're just variations in time. Okay. So in linear ODEs, the dynamics of small perturbation this means, remember, this is the dynamics of what we called yesterday zeta, 0, zeta t, from yesterday. Along trajectories, of course. Does not depend on the trajectory. On which trajectory? On the trajectory. We are going to do an example now. Or the initial condition. Okay. So therefore, what's going to be the FTLE? The finite time linear exponent is going to be what? So therefore, the FTLE, so this is going to be a scalar field, we know it, right? It's a scalar field over the initial configuration, but what is it? So, you know, if you have this scalar field, and this guy doesn't depend on space, it's just a function of time, a constant in space. Okay, so the FTLE doesn't depend on space. It's a constant in space, maybe it's more direct. Is uniform in space. Okay, is it clear? So basically, the beauty about this, and we're going to do an example now, is that basically linear system, if you want to have a new definition of linear systems, are systems that are not really able to say, yeah, I'm in this region of the phase space versus I'm in this region of the phase space. They just cannot make that distinction. Okay, it's very powerful. So they are just a little bit, less able, actually unable to distinguish different spatial locations. Let's do basically an example. How do you realize this? Let's do now a linear saddle, 2D saddle flow. So now I'm going to make it simpler, our system here. So we're going to say x dot is equal to minus x, y dot is equal to y. Okay, so basically you integrate this system and you're going to get basically that x of t is equal to e to the minus t x0, y of t is equal to e to the t y0, okay? Therefore, you can get df. I don't put the dependencies here, but what is df? It's just going to be derivative of x with respect to x0, so e to the minus t, 0, 0 e to the t, okay? X0. X0, Y0, right? That's F, that's X, sorry, so this is already gone, yeah, okay. Okay, so you compute the Cauchy green is just e to the minus 2, and the largest Lyapunov exponent is going to be e to the 2t, right? Because this transpose by itself is just going to be, having e to the minus 2t to the 2t. So this means basically that now you do this. So if you plug it in here, this is going to be basically e to the 2t. So it's square root e to the t. And basically the log of that is going to be basically t. Okay? And this is just t minus t0. T0 we are picking it equal to 0 here. So this would just be 1. What is that? So the Lyapunov exponent of this system, the finite Lyapunov exponent of this system is really the strength of this saddle. So if you would really put an alpha here, you would really get that FTLE here would be equal to alpha, which in this case was equal to 1. Okay? Everywhere. Let's see how beautiful, so this still may look a little bit, abstract, but let's do a very concrete example. Okay, so now let's we are here. Problem. So in X I go down, and here I go away. Okay, and now let's say that you want to understand the separation of particles across the x-axis. So what you do, basically you pick particle 1 is going to have y1 of t is equal to, is going to be e to the t times y01. Let's say that we pick this particle somewhere here at a distance from the x-axis, which is epsilon divided by 2. Doesn't matter, right? So this would be this times epsilon by 2. That would be just my y not 1. Okay, that's particle 1, or initial condition 1. Okay, and then let's pick another one. We're just gonna pick it here at distance epsilon 2, negative sign. So this would be y1, y2 of t equal to minus e to the t minus epsilon divided by 2. Okay, and let's say that we also pick that x1 is gonna be of t is gonna be equal to the e to the minus t times some x0. So we're gonna pick a particular x0 of this position. Okay, so this would be x0, and let's say that x2t we are gonna pick the same x0, because we are just interested in the separation. It doesn't really matter to have two coordinates, then you have to compute the norm and blah blah blah. Okay, so what is now the distance of these two particles? So the distance, so if I now do the distance between 1 and 2 as a function of time, is just going to be, well, these two are going to give 0 because they're basically exactly the same if I do the difference. And this guy, they will just give us basically e to the t times epsilon, right? So initial separation, final separation, okay? Right? I mean, that's basically, they are going to just, separate. Now I ask you, where is, in this space, this is the fixed point, remember? So in this space, where is the particular initial location x0, y0 where this separation is going to be the maximum? Guess. Huh? The origin, I mean, so that's the tricky counterintuitive stuff. The origin is, so this is the origin, I mean, so this distance that we just derived doesn't depend on x0. So the origin is as good or bad as any other point. If I pick two particles here, do it. This is going to be particle 3, particle 4. I initialize them with a distance epsilon with respect to each other. They will have the same norm. So basically, you pick two particles here that will separate with the same norm, with the same rate. They pick two particles here that separate the same rate. Because this is really the way you understand it. Basically, this linear system, okay, there is this origin, but the origin is going to be important to understand if you want to say, okay, where how does a single particle flow, right? But as soon as you're basically concerned about separation, this system is unable to distinguish any point. Okay, very important, right? So if you basically put a bunch of ducks, our tracers, in here, they will just separate everywhere in the same way. So if you plot this scalar function, which is the maximum separation of initial condition, is going to be a flat field that just increases with time. And the rate of increase is just the strength of this basically saddle, okay? And that's it. That's basically, this is it. So this is, so stretching and separation. Or stretching is just a stretching of, think about this initial condition as pieces of material. So stretching with separation of nearby initial condition are independent, is the same, uniform in space. Okay. Okay. This is very cool. So basically, this means that if someone gives you a data set, okay, so let's use this as an inverse problem now. If someone gives you a data set, a velocity field that you measure with the experiments, you don't know the equation, right? You don't know these guys. So you're never going to be able to say, oh, is this linear, is it pseudo-linear, etc. Compute the FTLE. FTLE looks pseudo-flat. You say this is almost a linear system. Maybe there is going to be a little bit of deviation, and then that means, okay, maybe in some regions there is a little bit of non-linearities. That means basically that I'm going to start adding small correction to whatever linear system it is. And the FTLE itself is also going to tell you, if you do this inverse problem, it's also going to tell you what's alpha. It's in the underlying equation, or that you don't know, right? Okay. Okay, this is, I think, a very interesting observation that you get it for free from the FTLE. Let's now go with computing FTLE. I'm going to call it now, for generality, from time ta to time tb at configuration or initial condition xa via finite differencing. Okay, computing FTLE via finite differencing of the deformation gradient. And we're going to do, just without loss of generality, we're just going to do an example in 2D. Guys, is this clear? If there are questions, please stop me. Otherwise, yeah.
We have taken particles along this axis.
Yeah.
So if we take, suppose, this along the y-axis, so maybe like this term will come as e to the power minus t.
Which one? Sorry?
So we have taken two particles here.
Yeah.
This is y-axis. So
Yeah.
we take two particles
Yeah.
taking the y-axis.
Yeah.
So I mean, this term will become e to the power minus t, the distance.
Yeah.
So I mean, they will converge.
Yeah.
So I'm not able to see like why this FTL is uniform.
Well, because remember, so the FTLE first of all is considering the largest separation. So this guy for free is gonna pick up where things will separate. Okay, but there is gonna be several Lyapunov exponents. If you take the smaller one, you're gonna get minus t. Okay. But in general, the thing is that whatever direction you remember what I said yesterday, basically df that evolves like this guy, df dot equal gradient of the velocity field evaluated along trajectories times df, the equation of variation. df is going to tell you any possible direction that you want to explore separation on is embedded in df. Okay, whatever you want to pick, solve df, and it has everything in it. And then it's very trivial to say that df doesn't depend on space. So whatever, it doesn't really care, whatever orientation you're gonna pick. The answer is that that particular initial fiber, whatever orientation it is not gonna care if you start it here, it's just gonna be always the same, the separation, okay? The maximum separation, you can say, okay, the minimum or the maximum convergence, which is the smallest eigenvalue, etc. Okay. Other questions? Okay. So what do we do to compute now the FTLE? In an example in which you cannot really resolve F analytically. So you have to define a dense grid of initial condition XA. Okay, and let me actually sketch it here. Well, maybe I'll put it here. So remember, I'm gonna put time here. Then there is gonna be, this is the so-called extended phase space. This would be, XA. So this would be our initial domain. Okay, and what you're gonna do this, and then this particle will travel until some time TB. I mean, the way really to realize this is, think about a deforming continuum. Okay, you grid now a piece of an elastic, sheet. Then I deform it, and this is going to be the deformed configuration. This is going to be the initial configuration. Okay, and they know exactly how each point in the undeformed configuration is going to be mapped to the deformed configuration via F. Okay. And the same is for, if you go in the ocean, you have a bunch of ducks, they will go somewhere else, okay, and therefore this is going to be our, final configuration. Okay, so you start from the initial configuration XA, and this is going to be XB, space, and then you grid this initial condition. So you're going to say, okay, now I want to, grid this. Well, this is what you're gonna do in the afternoon. Okay, so that's great. And let's say that you use a spacing of this grid which is called delta. Okay, and you just have to compute trajectory. So compute XB, which is just the advected image from the flow map starting at xa. So you integrate trajectories like we did yesterday. This is just the integral of the velocity field, whatever velocity field you have. And this is going to be basically a vector. We are going to need the entries of this. This is going to be x. Okay, so xa, any position xa is going to have two entries, the x coordinate, which is xa scalar 1, and xa scalar 2. This is basically the coordinates, denotes the components. Okay, so then this was the initial condition. The final condition is going to be basically x1, component 1 as a function of xa, x both, because wherever you go depends on both coordinate x, x1 and x2, the x and y if you will, xa, ta, tb. Okay, and then there's going to be another coordinate, which is the y component, which is going to be still a function of the initial condition ta, tb. Okay, this is very trivial. Okay, so basically, for instance, you start here. Let's say you start at this particular point, one particular xa, I don't know, xa number, I don't know, 10, and then this guy is going to arrive here, I don't know, at some point. So this would be the corresponding xb associated with xa. It's just the initial condition and final condition. Okay, so then what you do basically, okay, so this is basically what you're going to do. You're going to do it for all possible points. Now let me actually focus on the neighboring points of xa. So these guys will eventually go to some vicinity of these points, right? So let's say one is going to go here, one here, one here, one here. You agree, right? They will go. So this is going to be a condition that, another initial condition is going to be mapped here, another here. So eventually, this is going to be what's happening is something like this, just for this particular initial condition. Okay. Okay, so what do we want to do now? Is this clear, guys? Are we clear on the notation? Yeah. Okay. So then what what we want to do? We want to compute the deformation gradient. Use finite to compute df at any point, right? Okay, so what do? Basically, you pick this particular dA. Now this is the initial condition of f t a t b of xa. Okay, what is this? I'm just gonna put it here. So this mathematically would be the derivative of the first entry of f with respect to the first entry of x0, xa1. This is gonna be df first entry of the map with respect to xa second entry, or y if you will. And this is the same for the second entries. Okay, just the Jacobian. How do you approximate this function? This is going to be what? The first entry, we call it x1. So this would be just if you do centered finite differencing, this would be x1 evaluated where? At xa. At xa, actually now we have to expand basically the entries. So this would be the x component of xa. This is basically the derivative of xa plus delta, comma, xa1 plus delta, xa2. This would be just, the x and the y component of the initial condition, okay? ATB, okay? And then what do you get? Minus x1, where at xa1 minus delta, xa2, TATB, divided by 2 delta. Okay, I don't remember, guys, I'm missing if this is plus or minus. If you do finite differencing, is it plus or minus? Minus, yeah, okay. Okay, so that, this is basically how you approximate the derivative. Okay, now you do the same. So what you're gonna do here, so here you're gonna do x df1 with respect to x2a. So this would be now, okay, let me put it here. So this would be, actually, let me write all the entries so that this is basically, this is what you have to implement in the afternoon. So this would be, so x1 at xa1, now I have to perturb y, so this would be xa2 plus delta TATB minus x prime of xa prime xa2 minus delta TATB divided by 2 delta. Okay, and this is the same with x2. I'll just repeat with x prime going to x2. Okay, here and here. Okay, is this clear? Just find a differencing. So basically what you're doing here, you're saying, okay, I want to understand a derivative of f with respect to x. So then I can basically pick this guy, do the difference, and have an estimate about the flow map. X component is going to change when I step in x. And the same, I say, okay, how does this x component changes when I basically vary myself in y, in the initial condition, and then you do the same for the y component of this trajectory. Okay, and of course you can have even more sophisticated methods to estimate this df. It's really up to you. Okay, and a similar argument holds for x in n dimension. You can do this finite difference in any dimensions. Okay. Or an alternative to this is use the equation of variation. If your system is has many structures, and there is some regions that will separate very much, some others that will separate less, so there is a lot of heterogeneity, you might want to use the equation of variation. So once you do f, so this you have to do it for every initial condition, for every xa initial condition. You have to compute this matrix, df. Okay, once you do that, you compute, basically you construct C, which is just this simple, df transpose df, and then you compute the largest eigenvalue, and then you compute the FTD. Okay, and that's it. Then you have a scalar field over all these initial configurations. So basically it's going to be a scalar field over your initial domain. Okay, and the FTD is basically very simple to interpret. You're going to see a lot of examples later, maybe in 20 minutes or in 20 minutes, and even more in the afternoon. So it's going to give you a scalar field that tells you how much this separation, what's the maximum separation for every point in your initial configuration. It's going to tell you how much two initially nearby particles will maximally separate, the rate of this separation. Okay. Okay. Let's do a little bit, a few more considerations. If there are questions, please, guys, just speak up. Okay, so some observation. I'm going to go a little faster. So when you start at the initial time with, this is basically your initial position, a particular XA, this is the neighborhood. This guy usually grows by, let's say the guy goes, it comes like this, right? After you do the from up. Okay? This separation can happen. So there are two contributions that allows two particles to separate. Two nearby initial conditions to separate. Let's say that this is what happened, right? There are two contributions. We already know that this direction is the largest eigenvector of Cauchy green. Okay, so you already know which direction. But this separation can happen in two ways. One, let's say this is basically the final separation. So the final. This is the initial. Okay, this separation can happen in two ways. Basically, it's a combination of it's going to be a combination of anisotropic deformation at constant volume or area in this case. It says, okay, I have a little initial neighborhood. I'm going to transform this circle into an ellipsoid, and the area of the circle is the same as the area of the ellipsoid. That's basically just an isotropic deformation. Okay, so this anisotropic deformation plus separation due to isotropic deformation. These 2 points, they will get separated if you just have an isotropic growth, plus contribution or separation due to isotropic deformation. Okay? And the FTLE contains both. You say, okay, there is a combination of this isotropic growth and isotropic deformation. You care what's the maximum separation. The FTLE is going to already consider both of them, and that's the sum. Okay, very, maybe a detail is that if you would just have a field in which you have differential growth, let's say you have a piece of material with differential growth, the situation would just be isotropic deformations. Okay, what would be the FTLE there? It's a delicate question, but think about it. So the FTLE there would not, strictly speaking, it would not be defined because you are trying to understand what's the largest eigenvector or eigenvalue in the of the Cauchy green that describes this deformation. So the fact that here there are no distinct eigenvectors because all the eigenvectors will stretch in the same way. So that means that Cauchy green or the DF will not have distinct eigenvectors. Right? Because the eigenvectors, remember, is just picking up the major axis of the ellipsoid, and the eigenvalue is going to tell you the ratio between the major axis divided by the initial diameter, right? So strictly speaking, the FTLE is not defined. Whenever you do a calculation with noise or whatever, as soon as, also if there is basically the majority is driven by isotropic deformation, the noise will always pick a particular direction, and you're still going to get a very good result because eventually you're going to pick this separation. Okay, that's just a very minor detail. Yeah.
So basically, in this case, there is no concept of the largest separation or something. I mean,
they are all the same. They are all the same. Yeah. They're all the same. But the noise, it could be numerical noise or could be experimental noise. They will tell you, it's basically the eigenvalues are all 0.9, 0.95. Eventually, you're going to pick something that is around 0.9, which is what you want in the end. But if you do the calculation analytically, you're going to get stuck because basically you cannot compute the largest eigenvalue of Cauchy green because there is not one. Okay, but this is just a detail. Yeah.
So in the first case, when it's stretching, does it mean in one direction we have positive eigenvalue and one direction we have negative eigenvalue?
It's a very good point. Yes, it's more than positive and negative. One is, remember, Cauchy green is positive definite.
That's what my
Yeah. So one is larger than one is smaller than one, but still greater than 0.
Exactly. So that was my confusion. So if a positive definite has to have one positive eigenvalue.
Yeah.
Then how can one direction it can shrink?
can shrink, because remember, so this, it's a very good point. So zeta t is equal to df zeta 0. Okay, so if you want to understand if this goes, so we already know, actually, if I do this, is the norm of this, which is basically, how do we say, okay, I mean, let me do this, right? So I do the ratio, and the ratio is the square root of lambda max, of lambda, so one, the eigenvalues of Cauchy-Green, okay? Well, wait a second. Let's say the max of this over the possible zeta 0 would be lambda max. Okay. Now let's do you do the mean of over different zeta 0. This would be square root of lambda. Okay. But this basically, so if this is less than 1, that means basically that you're gonna shrink. You don't have to be less than 0. This is a difference, because this is basically zeta t equal df zeta is a map. It's not a differential equation. If you would have this zeta t dot equal to df d capital F zeta, then the rate of shrinkage or expansion would be positive or negative, and those would be associated to the eigenvalues of the rate of strain tensor. Okay, yeah. Okay, and actually, because you conserve volume, you also know that the determinant of 4. So in this case of volume conservation, you also know that the determinant of df is equal 1, and therefore also the determinant of Cauchy-Green is equal to 1. Because df transpose df is basically Cauchy-Green, and therefore in 2D, or in general, if this is true, that means that the products of all the eigenvalues of Cauchy-Green should multiply to 1. So if you get the largest one, you have for free the smaller one in 2D. Okay? Yeah. Okay. Okay, so a very quick comment. Here we looked at the largest separation. So remember, at some point we said, what do we actually do with this tensor? Because so it's hard to visualize. So we did a choice, and we said, okay, let me actually look at, out of the possible neighboring initial conditions that I have, I'm going to pick the one that is going to separate the most. I made that choice because it's very useful to know. But in general, you can also extract other information. You can also ask, wait a second, I don't really care about how much the maximum will stretch. How about you tell me how much this volume is going to expand or shrink? That's another scalar field, okay? And, you know, this is the observation 1. So observation 2, if interested in volume changes instead of largest separation, this is an information that is contained in the determinant of Cauchy-Green. Okay, we can go over it, you know, in the afternoon or later, but it's also very easy. It goes from, you know, this is basically is the Lewis theorem or the Abel's theorem for you know. If you want to know, you know, there is a lot of more information in the F. Okay, so that's another thing that you can inspect with these techniques. 3, also very important, F, TA, TB, in general, when you have a time-dependent system, is you know, depends on, it's called, basically speaking, is a 2 parameters family of maps. So that means basically that once you fix the initial condition, TA and TB are both important. And we're going to do example on how to understand their importance, and this is associated to a question that someone asked yesterday. They asked, oh, but how do I pick this TA and TB? We are gonna do this in a second, okay? Okay, so let me, if you should ask questions also when I erase, so we optimize. Questions?
I don't understand the hyperobjectivity.
Yeah.
Where you said that one cannot strictly define the exponent. Because, so it's a degenerate alignment is there, right?
Yeah.
So then all eigenvalues are the same.
Yeah.
Then it is not equal to
Yeah, true. But that's a very good point. But if you do, let's say, if someone tells you what's the maximum eigenvalue, there is no maximum eigenvalue. So all the directions are the same.
okay.
Strictly speaking, there is not really a maximum. Maximum also means distinct. Okay, so there is not that, but you are right. So intuition, I mean, your argument is perfect. So that's why I said, look, I mean, whenever you do it with a computer and not really pen and paper that you have everything analytic, something's gonna speed up a value which is just your tolerance of the MATLAB solver that you're using to that accuracy, which is basically you got the same. You guys, yeah. Okay, other questions? Okay, so now let's do let's introduce the notion of Lagrangian coherent structure. Okay, or LCS, and specifically here we're just going to focus on attracting and repelling LCS. Okay, there is no time I can tell you. There is a lot of work on this. You can see a review article from George. It's an annual review of fluid mechanics from 2015. I think that George is also a book, and there is a lot of other, people that work in this field. There was an article from Sean Sheldon and many others. So if you look at the review article, there is a very good set of references. So I don't want to, not give credit to other people, but this and the references that are inside should give you a very good idea of who contributed to this field. Okay, so what's the question now? So okay, now we have that, the FTLE is just, okay, I'm just going to use interchangeably TA, TB, T0, T, XA, but it's the same, right? So let's say the FTLE basically, let's actually keep TA, TB, XA is local. That means basically with respect to XA. Okay, so it's okay, you start at any point, XA, XA1, XA2, XA3, not the components, just different points now. And it's going to tell you, okay, how much do I separate maximally? How much my neighboring points would separate maximally? But the question is, okay, how do we identify global structures? Okay. Okay, what's the setup? The setup is what I already told you there. So the setup is basically that we are going to have an initial configuration, final configuration. So this is TB, TA, XA, XB. Basically, this is basically initial configuration, final configuration. Okay, and T, let's say the TB is going to be some TA plus a certain integration time or time scale of interest. Okay, and now I'm just going to provide some intuitive definition. Because if you want to formalize them, there are different techniques to formalize them, but it doesn't really change the story. Okay, so we're going to define repelling LCS from the time interval TA, TB, XA as basically, actually, let me write it in red. This is going to be a ridge. This means basically a set of points with I value. With I values of the forward time. We're going to go back to the backward time in a second, which we're going to call forward FTLE, which is the FTLE that goes from TA to TB of XA. Okay? So what is this? Let me actually do a sketch here. So this means basically that you compute this FTLE, so you initialize your dense grid of particles at XA. At back time until the particular time XB, compute this final difference in Cauchy green lambda, compute the FTLE. The FTLE is going to be a scalar field over your initial configuration, just like a temperature field. And then let's assume, for instance, that this scalar field, now if for instance I project XA here, okay, we're going to do this with the slides, but let's say for instance you get some sort of a scalar field like that. Okay, so that means basically, and this is my scalar field over XA. This is now my forward FTLE, or the forward FTLE, TATB, XA. Okay, so that means basically, okay, here I have very high value. That means basically when I project this back on my domain, I'm gonna see this ridge. Okay, what happens to this ridge? So I'm gonna print this ridge here. That means basically that any initial conditions that were initially close, so there are going to be 2 points here, 2 points here, that will eventually separate by final time. I don't know, here they will get separated. Okay? That means basically that this ridge, that is the ridge of this scalar field that is defined over the initial domain, is going to mark all the points in my initial configuration such that when I arrive at the final time, they initially were this far apart. Now they are this far apart, so they are basically maximally separated. So this we call it a repeller, right? Makes sense? Okay, so this is basically, so this thing marks the set of initial points means basically XA points at the initial time, TA, whose nearby points, these guys, at the opposite sides of the repeller, which is this guy, will distinctly separate by time t, TB. Distinctly means basically that if you pick any other 2 points here in the vicinity, it will separate less, because the FTLE is maximum here. So this is going to tell you, look, at this region, there is some nearby points which are going to be aligned with the, in the direction of the largest eigenvector of Cauchy green, which you can also, print if you want. It's going to tell you, look, these guys are the ones that will maximally separate. But here, also if I go now, let's say if I just go nearby to this ridge, let's say I start exploring this guy, I project this line here, this guy, points will also separate because you still have some, greater than 1 level, the greater than 0 level of exponent, but will separate less. So that's why you mark basically this as a repeller or a ridge, because this is the regions where things will separate maximally. Okay? Is it clear, guys? If not, just ask. This is very, it's very normal to have questions. Okay. If you hold a little bit, we are going to have some slides, and then this should become more visual. Okay. Okay, so what I want to do now, I want to go to attracting LCS. And actually, let me print something else here. Is it clear, this initial final configuration? So the way you have to think about it, this is really because these guys, they live and they want Lagrangian coordinates. Remember, once you fix the initial condition, you have no more control on when you're gonna go. Let's say, for instance, everybody starts of these edges of these tiles. Okay, I start here. There are other people that start nearby, and then someone somewhere, Anupam is gonna drive us like with a joystick and say, okay, I start here. I pick this initial condition. My fate is done. Because I'm gonna say, okay, I'm gonna go here, and then I'm gonna go here, etc., and that's it. So once I pick that, at this time, let's say, which is maybe 1 second after I started, I cannot decide to go explore the velocity or the temperature here. I can't, because I'm done. This is basically my fate. So once you pick your initial condition, that means basically, let's say that you have now, let's say you grid your initial condition. And later, think about this as everybody, we all start at this, the intersection of the tiles. Once I go a later time, what happens is that, okay, there is still going to be these coordinates. But the problem is that, okay, now this grid is deformed. Okay, it's still going to have the same number of lines. I don't know. Okay? But that's it. So once I pick this guy, and this guy, I don't know, arrived here. Okay, so this is basically now the final configuration. So this would be just, F, TA, TB of that particular XA. This was the XA. Okay, that's basically very important to have in mind. And now repellers are defined in this space. It's a scalar field over this space. It makes sense because you want to say, hey, where are the guys that will start nearby? We are gonna start equally spaced. Where is the ridge I should draw such that when Anupam drives us, we're gonna separate? Where is this separation line? Okay. Okay, and this is going to become now clear in the attractor setting. Okay.
In the linear case vector that we saw initially.
Yeah.
So can we define these repellers?
Try. I don't think you're going to succeed because there is no structure. You see, it's an excellent point. What you're going to get in the linear structure, you're going to get this as the FTL is. It's going to be something like this. Scalar field that is the same everywhere, and the only thing you can play with is the height. It is going to depend on either the strength of the linearity, your linear stretching, and time. Actually, time not, because you're scaling time with FTL is an exponent. So this is beautiful because it says, hey, a linear system is never going to be able to tell you, look, there is this structure here, this particular ridge. Everything is the same in space. We try. So this afternoon, when you start playing with it, you start with any velocity field that you want. It's more complicated, and then try a linear velocity field, compute it, and then you see this flat thing. So there is no structure basically in space. That's basically what it means. So now let's define an attracting LCS. Attracting LCS from TA to TB at XP. Now we're gonna clarify why this is the case. Is basically a ridge, a set of I points, blah blah blah, like there, I values of backward time FTLE it means basically the FTLE needs to be computed from TB to TA and is going to be based at XB. Okay, actually let me write this in red, like there. So this is going to go from TB to TA at XB. Okay, and of course, by the way I draw this, chronologically TB is always greater than TA. So this is the chronological time. Okay, and we're gonna do this. So this marks the set of final points XB at TB that or towards which initially I mean XATA particles, far away points maximally converged by time TB. Okay, sorry, this may be a little bit counterintuitive. We're going to do a sketch now. The backward, and therefore, this backward the backward FTLE is computed from TB to TA, XB, is a scalar function, is a scalar field over the final position, over the final configuration. Okay, that's very important. So why is this? Why is this? It's just a numerical or a conceptual construction, because basically, now let's go back to our space, and the chronology is still always that this is XA, this is XB. Okay, this is basically XB, TB, TA. Then you say, okay, you know what? What I'm gonna do now to compute this mathematically, we can just use all the formula that we have so far. It's just that now your initial time is gonna be TB. So what you're gonna do now, you're gonna grid a very dense grid at the final time. The final chronological time TB is gonna be the initial time of your backward integration. So you compute this, and you compute all these particles back, right? You compute all the trajectory backward in time. That basically means you grid here, and you flip the sign of the velocity, okay? And what you're gonna have, so you compute that, so you can basically F, TB, TA, XB, DF, Cauchy-Green, but this is now all based at XB. Okay, and then backward FTD, which is now also based at XB. Okay, now what happens when you have a ridge in this space at the final time? This is gonna tell you, look, I mean, here I had two guys near me that maximally separated. So now they arrived here. I don't know. Of course, this holds for any point on this curve. I'm just going to represent two, right? So basically that means that separation or maximum separation in backward time is the same as maximum attraction in forward time. That's why. So basically you just do this trick, you go just backward in time, and then it's exactly the same as what we have for the forward one. But the interesting thing is that now everything is defined over the final configuration. So this scalar field that you're going to visualize, if you want to see where the attractors are defined over the final deformed configuration. So it's a scalar field over this deformed configuration versus a scalar field over this initial configuration. But the numerics is very simple. It's just the same. You really have to use the same code and just initialize initial conditions at the final time and just flip the sign of the velocity when you do the integration, and then this is the same formulas to compute the case. Okay? Yeah.
For attracting structures,
Yeah.
what if one looked at the smallest eigenvalue instead of maximum? So we do the forward time.
It's not so simple. Yeah, it's not so simple. So you can sort of connect the two. It's not just looking at the smallest eigenvalue. Yeah, it's not so simple. It's basically you can connect the two. There is a paper which is called computing attractors and repellents from a single computation from FTLE, from Farazman, Mohammed, and George. But it's not so simple. Yeah. Okay. So what are the notes? So the notes is that FTLE requires, so forward FTLE requires a dense grid of initial position at XA, the initial configuration. This requires a dense grid of initial position at the final configuration. So let me actually write some notes. So forward FTLE, forward advection requires forward advection and a dense grid of initial conditions for the integration at XA. This instead is the opposite. Backward FTLE is required backward time advection, flip the velocity of the sign of the velocity, dense grid of initial condition at XB. Another very important note is that this is crucial. You can compute the largest eigenvalue of Cauchy-Green, okay? But to ensure that that you are going to have separation, you have to ensure that this largest eigenvalue is greater than 1. Okay, because think about it. So I can have basically this blob that transforms into this. Okay? So there is still going to be a largest eigenvalue and the eigenvector of Cauchy-Green, okay? But these particles, instead of getting more far away from each other, they actually got closer, right? Because eventually here, that means basically that there is going to be a very significant shrinkage, isotropic shrinkage, that is not going to allow the anisotropic one to dominate. So basically, this is very important, right? It's very easy to check. So to have attraction, actual attraction and repulsion, so repulsion, you have to ensure that the lambda max TATB XA is actually greater than 1. If it's not greater than 1, it's not going to mark regions where things will separate, okay? It's still the regions where things will, there is going to be the largest axis of this ellipsoid, but then, it's not going to mark separation of initial conditions. And this is the same. So to have repulsion, to have attraction, you have to ensure that the lambda max in backward time is also greater than 1. So this is very important.
So you said that the determinant is always 1.
No, it's always 1 if it's basically incompressible, volume preserving. Yeah.
So in those cases, then this is always satisfied itself.
Very good, very good. Yeah, very good point. Yeah. And it's not satisfied at points that start as circles and stays like circle. And those are called singularities. Okay, so we have several papers on this. And if you look at the topology of these singularities, they are singularities of the direction of the eigenvector field of Cauchy-Green. The eigenvector fields are exactly like nematic fields. And what we found very recently is basically the topology of these singularities are exactly the same as the topology of the topological defects in active nematics. Okay, okay, but yeah, so that's what you said. Okay, so the last thing we want to do is, and now we are gonna display a few of these fields, is it may be interesting. So it could be of interest. To understand, to visualize which set of initial condition will go to the attractor, will converge to the attractor. And you know, of course, there could be also multiple attractors, and some sets will go to one attractor, some sets will go to another attractor. So this basically means that, you know, this means, i.e., the domain of attraction. Okay? So this basically means that, let's say, if this guy is something where things will converge, you want to ask, it could be interesting to ask, hey, actually tell me, what's the set of initial condition that will actually converge to this attractor? So that means basically that this attractor is going to suck in all this big set of points. Okay, so that's going to be the domain of attraction. Okay, we're going to see it in a second, in some real examples. The way to compute this is basically you just transport or visualize the backward FTLE. Remember, the backward FTLE is a scalar field over the final configuration. You know, it's like here. This guy is here. I just flip this plane. I put XB here, and this guy is some sort of, you know, a ridge here. Okay. But the important thing is to realize basically that any point in this XB space is associated to one scalar field, right? This is really a scalar field for every point. Okay, just a scalar field. This you can also think of as, I don't know, scalar field of XB. Okay. Okay, how do you visualize? If you want to understand where these points are coming from, you just passively transport this field at the initial time. So how do you do that? Just use the flow map. So you're gonna have, okay, so now I have this scalar field. Let me actually notation of a little bit annoying or long to write. It's going to be TB, TA, XB. But instead of now visualizing it at XB, I want to visualize it at XA associated to that XB. That means basically now I'm going to use the flow map to transport this point from TB to TA of that particular XB. Okay, and that's basically really the XA associated to that XP, right? I mean, it's just, you know, think about each of us starts in a configuration, and each of us have a particular temperature, or let's say hats of different colors. We are in the deformed configuration, then we go backward in time, and we are going to go in our initial grid, and each of us is going to be with our own hat. That's the same. The hat is just going to be a color or a scalar field. Okay. Okay. So, shall we do the slides, or it's too late?
No. This is definitely.
Okay, yeah. Okay.
One question here.
Yeah.
So these will be, suppose if you go for like slightly chaotic flow,
Yeah.
and we know that it breaks the time reversal symmetry, right? So, so backward and forward will not be the same.
They will be the same. These are the backward and forward of fluid particles. Also, if you have a turbulent flow, if you basically start with if you throw a duck in the ocean, this duck basically is going to move with its own trajectory. If you revert the flow of the ocean, you're going to go exactly to the initial condition, modulo the errors that you can do with accuracy, etc.
But it's in average flow, it's non-linear term kicks in.
Yeah, the problem is what you are considering is the evolution of the velocity field as a dynamical system. This is not the velocity field. This is the particle position advected by the velocity field.
But suppose I have a very stupid example. Like if you take improp,
Yeah.
there is this famous experiment, right? When you change the viscosity,
Yeah.
for smaller viscosity, if you start
Yeah.
it, you will see that everything will spread.
Yeah.
You try to come back, you will not be able to come back to your initial state.
Because-
Whereas if you increase the viscosity by adding glycerol or something,
Yeah.
you see that of course, improper starts to deform. And once you reverse the motion,
Yeah.
it's going to come back.
Because if you do the inverse calculation of what you just told me, you're doing for particles, for molecules, you're doing a Langevin equation, not a deterministic system. Because the diffusion is gonna break that.
Right.
But the motion of particles in general, when someone
So it's not only flow, but there is
there is diffusion. The diffusion is gonna break that. Yeah. Yeah, it's a good one. So can I connect maybe quickly the?
Yes.
Yeah.
Or because this is important. So if you want more time, we can do it after break because this is more crucial than what I'm going to do. So
Okay, so I'll continue that. So then let me actually before we do the we're gonna do the examples, some visual examples later. What I want to basically do as a last thing, some very practical question which also came yesterday during the seminar, and it's actually a general so some rule of thumb of how do we select a TA and TB. Okay, so the question is how to choose TA and TB. So basically, someone gives you basically a data set. So input, you get a data set. You get basically some velocity field as a function of x and t. From some initial time, it's a t0 data set to some t-final data set. Okay, so the way you pick TA and TB really depends on your problem. Okay, for instance, example one is something like I don't know. An example could be in the ocean. You want to ask, I want to understand in the ocean. Someone gives you all the velocities of the ocean. The emergence of 1 hour attracting structure. In the sense that I go in the middle of the ocean, I throw a bunch of things, and I want to collect them in 1 hour. After I threw them, where should I go? Okay. So, question one would be study the emergence of 1 hour attractor over attractors. Okay, so what do you have to do basically? So attractors means backward left-ly. And what do you have to do? You have to pick a Lagrangian time scale of interest. Integration time, Lagrangian time scale of interest equal to 1 hour. Okay, and then what you have to do from this data set that you have available, so this would be really the T0 that you're going to have, this is going to be the T final. what I'm gonna do, do you have guesses on what we should do? So you want to understand where are the regions such that a distribution of floaters get attracted to from 1 hour before. Okay, so what you're gonna do, basically, you start scanning. The first time you can interrogate, if you want to answer this question, it would be T0 plus 1 hour, because you can integrate backward for 1 hour. You cannot provide this at T0 because you don't have 1 hour data in the past, right? So you're gonna get basically at this time, and then you use this, which is basically T minus 1 hour, which is happens to be T0 time, but this you just start scanning future time. So this guy is going to be another, this would be, I don't know, a T1. You're going to get a T2. It is going to be from T2 to T2 minus 1 hour. This is T1 minus 1 hour. Okay, and blah, blah, blah. And you're going to, do this at the resolution you want. Okay, so you're going to get this scalar field. It's going to change, and it's going to tell you, hey, if I want to throw it, let's say this is basically noon. Okay, if I want to throw it 1 p.m., look at the scalar field given by this guy. If you want to throw it 2, look at the scalar field given by this guy. 3, 4, etc. That's it. So this is basically, so this integration time is going to tell you, look, what are you interested in? Where things go over 1 hour or 2 hours or, okay. And then this is gonna just say that, look, I mean, this system is a dynamic system, so things will change over time. So of course I have to explore the relevant chunk of time. And then I can redo this exercise. So therefore, this is gonna allow you to explore all the dynamics of this system, okay? And another example could be this one. So, example 2 would be, study the emergence of attractors over time. Okay, so this we're gonna do it in the examples later, but this basically means that, okay, if you want to understand where things start, where things accumulated, and you don't care when you throw stuff. So if things were already floating in this system, and you want to understand where do things accumulate, most likely, okay, then what you're gonna do, do you know the answer? So this is still the same, initial data. Then you're gonna say, okay, you know what, now I'm start exploring this chunk of data, so I'm gonna get T, the backward time is still gonna be an attractor, backward time from time T to time T0 of X of T. So every time I'm gonna say, okay, I'm gonna use all the data I have available, because I'm interested at any time. Say this could be, I don't know, T1, this is lambda T2, up until the initial time T0, okay, until I go here. Okay, this is gonna tell me, look, where are the most developed or sharp attractors over this time interval, okay? And this is very cool to explore, because for instance, let's say you have a dynamical system and you see that basically, I don't know, at time 5 you start seeing the emergence of attractors. That means basically that, some forces or processes are such that it takes 5 hours from these attractors to manifest, okay? And before they're not there yet, right? This, of course, you have to sort of disentangle all the possible cases. It could be basically that maybe at some particular point, the velocity is so strong and so in a particular configuration that it's going to generate a lot of attractors. So maybe from 3 to 4 I develop this attractor, and of course I'm going to see it if I integrate up until t0. But that you would also spot it like this, because that would say, okay, you know, from 3 to 4, so when I'm 1, 2, 3, 4, so in this field, when I would observe this field, I would already see the emergence of these attractors, and these attractors was not here. Here was no attractor. That means, okay, it's really emerged from the velocity or the dynamics from 3 to 4. Or if you start seeing it that is, you know, here you say, okay, you know, it's actually very shady here, etc., and then it gets stronger and stronger. You know, here is stronger and here is more stronger. Then you say, okay, you know, this is building up. It takes time for this attractor to develop. It's actually forming over time, right? And this you can do basically just with, you know, any data set. So playing with the integration times, initial time and the integration time, so basically T, A, and capital T, allows you really to explore all the possible dynamics that is in this dynamical system. And, you know, just, you know, as a final conclusion, think about it, how powerful this is, right? To do the little, you know, to compute the stable and unstable manifold of that very trivial fixed point, you have to do a lot of work. It's constrained on the fixed point. It cannot be a system that is explicitly time dependent, okay? And it's only allowing you to understand where things go over infinite time. This, you can use it for anything. Okay, and we're going to do a couple of examples later in, you know, I'm going to show some examples, and then you can just run the code that we have available for any, you know, type of system that we're going to do it in the afternoon. Okay. Okay. Questions? Yeah.
So it can be done for any data set, so it can be compressible in complex.
Anything. Yeah. Yeah.
Flow can be.
Yeah. This could also be neural dynamics. It could be also neurons. You can, you know, the FTLE, you can compute it in any dimension. It's just going to be a scalar field in any dimension. 3 dimensions, 10,000 dimensions. Okay. Yeah. Okay. Yeah, we'll continue with some slides later and also in the next days. We have a lot of examples. Okay. Yeah.
So we can go for it. So so in the next examples, what I will do, I will start with the trace of hydrogen, but then I will show the examples where things get attracted. Space is actually contracted. So one can employ these things too.
Yeah, for sure. Yeah.
So this first week plot streamlines of the problem you are discussing.
Yeah.
So one is this Jacobian that we have in the first week.
Yeah.
Can I also do this?
Yeah, we can also do that. Yeah. violent. And in fact, basically, think about it. So if you have a velocity field that is quadratic in it working? How about I try this? Is it good like this? It's not coming. Okay. Or shall I just? Okay. So. Okay, just. How about I do just second screen only? Or no, maybe it doesn't work. Okay. I'm just gonna do this. You maybe. Yeah. Yeah, the issue is that. Oh, actually, maybe. Can you see that on your screen? But can you manipulate the things? Can you click on stuff? Because I don't see the screen. So it's oh, maybe I just go here. Or maybe I just go here. Yeah.
You can see.
Okay. Okay, I think if I now, because if I do this, it doesn't really go presentation mode. It just goes here presentation mode. Yeah, you see now it doesn't. Shall I actually connect to the Google link and share my screen?
Yeah, but the video is separate. Recording.
Oh. Okay, so actually, can I try? Let me try one more thing. If I do just. Do you see it now?
Yeah.
Okay, so that's good. So I just don't see it. It's great. Okay. 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 Shall we, what time should we start?
We can start.
No? Okay, guys. So I want to do some examples of what we've seen so far, and maybe we will focus on attractors, repellers, and domino attractions, and so we're going to look at this system. So this system is basically a biological system, and this is basically the chick embryo, an egg. There is the yolk, which is all the nutrient, and sometimes you can see this little white disc. This is basically the embryo.
Can you see the naked eye?
Yeah, I saw it. So when I go to the supermarket, I don't see it. But when I went to Cambridge to this experimental collaborator, I really saw it. So I don't know if these eggs that they buy, they are different or well, there is a catch. It's basically that you don't really know where it is. Within, so maybe you have to rotate a little bit the yolk, or it's but it's there. So basically, this is basically this disc. This is the real picture.
Color different. Yes.
Yeah. Maybe we can lower the lights if you don't fall asleep.
So in the actual use, you can see the color gradient, and you can determine.
Yeah. You can. It's really this. This is really the embryo. So the embryo is this little disc, and which is here. And in these first 15 hours of development, the embryo, this is basically, there are around 60,000 cells. It's circular, and then it becomes pear-shaped. And this is where you establish your anterior-posterior axis, which is the main body axis. And this stage is called gastrulation. Is very important. We're going to maybe go back to this example in the next days. But for us, the important thing now is that, okay, you can basically put this set of cells, again, 60,000 cells. This is about 3 millimeter wide, the diameter. And then you can, at least, our collaborators can measure this with confocal microscopy and can see how these cells are moving like a fluid, okay, or like a flow. Okay, so this should play. Yeah.
There is a question online.
Oh, yeah.
So do you practice it now?
Yeah. Can you? I mean, I was, but now I.
So we don't know. So if we start with a random configuration, we know that they will phase separate and they will become dense and dilute. Now I am wondering that where will the dense phase will appear? Will that be able to tell the Lagrangian constant?
Yeah. So I think Anupam is going to do something in the later. But it also depends. Are you going to provide one velocity field for all the particles, or velocity fields that are distinct?
Time frame. Yeah, time frame.
So basically, there will be Lagrangian tracks. So Mitro,
but the Lagrangian tracks will be. So do you have two phase velocities? or just one single velocity?
Just one single integrated velocity.
Okay, so then if you have one single velocity, it will show up. Yeah, wherever you have phase separation, I think you will have separation of particles.
So Mitro, the thing is that when you have these like active agents and when they start moving, so of course we cannot predict where it is going to be in space, but if you have tracks, you can, because tracks will give you the information where they are going to be, right? So so you have to look at the whole track.
Tracks will give, but let's say I am only giving the data before meets. Will it be able to tell that the dense phase is going to appear this position?
Yeah, I mean,
I'm saying that the dense phase is already formed, but I'm saying that the forecasting thing.
Yeah, so this is exactly what Matteo was saying, the build-up thing, right? So in the board, you may not be able to see, but in just before finishing the lecture in the first half, what he said that there will be appearance of this structure, attracting structure, and there could be a sudden appearance or there could be a build-up to that structure.
Yeah, no. So basically, Sumitra, the answer is yes. So these are really, they will, so even when by bare eye you're not going to see separation, because this basically, so this will capture this onset, or what you call, prediction,
That is the question.
as early as possible.
Yeah.
As early as possible. In fact, we have a paper which I think is going to show up now in the slides in PNAS, in which we show that you can see the emergence of attractors much earlier than was expected to exist, just because of what you're saying. So you start with these tracks, you don't know where it's going to form, but then you say, okay, there is a footprint here. And then people, maybe in this community at least, the idea was that these structures to manifest, you really would need to wait for hours, but even after half an hour, there is already there a footprint of it in the data.
Yeah. That was my question, yeah.
Okay.
Thank you.
Okay, sure.
Okay, I have a follow-up.
Yeah.
So of course one can use this technique, but one can also use all these neural networks to predict, right, if a coherent structure is going to form. So what is your opinion? Which one is going to...
Yeah, I'm not an expert in neural network, but this is very interpretable.
Right.
It's very robust.
Interpretation will not be there. If you just say that, okay, this is one structure, and then tries to predict, and you can do prognosis.
This is there. This is very robust. A neural network, I don't know what you're gonna get, because the lack of interpretability then is gonna be hard to say. Okay, is it?
But in terms of onset, it can at many times. So one can actually check that which one is performing better.
Yeah, so for instance, we are trying to look at variational autoencoders to extract features, so basically to reduce dimensionality of these FTLE fields and do a kind of a morphometric analysis of embryos. But the big challenge there is that you really need a huge amount of data. And in development, you don't have it.
Yes.
So that's another bottleneck. Right. But different questions.
That is a very important point.
But it's an interesting point. Okay, actually, I forgot that this is Anupam's slot to present, so I just have to speed up. But I think it's going to convey. This example has all of them in it, so I think it's the important one. Okay, so this is just a little bit of the context, but we are going to learn more about these systems in the next days. So I just want to say this is our velocity field. Okay, now it's cells, but it doesn't really matter. Okay, so just to give you, to have a context, velocity field, you can look at basically the microscope, and this is what you observe. It's just a sheet of cells. This is the field of view of the microscope. This is how these cells are moving. That's the formation of this anterior-posterior axis that I showed you before. Okay, the flow is mostly two-dimensional, as you can see here. There is a little bit of three-dimensionality, but very negligible at this stage. And therefore, you can just do PIV on. Oops, 1 second. They should be basically. You can do. Now, how do I go there? Oh yeah, here. So you can basically do PIV. So, and you can just compute the velocity fields of this motion of cells with just PIV and confocal imaging of cell boundaries in this case. Okay, so what you want to do now, again, we are just going to apply what we said in the morning. This is my data set. It lasts for 12 hours, okay, so 720 minutes. And what we can do basically is you know, we're going to do exactly this study. So I'm going to show first, I want to see the emergence of attractors over time, okay? So first, I'm just going to use all the 12 hours of the data set, and I will show the attractor field, which is basically the backward FTLE field at the final time. This is when it's high, it's going to tell you where things will accumulate, okay? And this is basically this field. So the field is very high, so this is basically the finite time Lyapunov exponent, and there is a very sharp ridge of this field behind this dot. It's going to become clear in a second, but you can see there is a very orange ridge. That means basically that there is going to be a very strong regions where things will get attracted, and this is basically this streak, which is basically this anterior posterior axis. Why? Because when cells reach this region, then will internalize. They will just go into the third dimension, okay? So basically what happens in this, I'm just going to use this for a second, but what happens in this case is that the embryo is transforming from a two-dimensional layer, and then it has to form an anterior posterior axis and left-right symmetry, and then it has to start internalizing cells to create in three-dimensionality, you know, organs, etc. This is the first time in which you start forming this three-dimensionality, which basically in the dynamics of the 2D plane, that means that cells will go to this line and then will ingress. So this will be an attractor for this two-dimensional dynamics, okay? So this is basically now the attractor using 720 minutes. So basically I used all my data available. So then what you can do, you say, okay, you know, let's compute now the repel. So let's actually compute the domain of attraction. So what I want to do now, I transport this backward FTLE field, and instead of visualizing the deformed configuration, I'm going to visualize it in the undeformed configuration at initial time. Okay, if I do that, it's very neat because it's going to tell you, look, at initial time, all these cells will internalize and ingress into the attractor. This is a very beautiful way to compartmentalize your domain. It's going to tell you, look, all these cells will form the attractor, the domain of attraction, okay? So this is basically the embryo at time 0, the onset of this process, which is called gastrulation. This is the after 12 hours, which is at the end of this gastrulation, where you form the streak, okay? And then let's compute now the repeller. Oops. The repeller, so the forward FTLE is still going to be a scalar field at the initial time, and then you're going to have two repellers. One, this repeller 1, that is basically separating all the extra embryonic cells from the embryonic cells. So if we play again this video, you will see basically that the outermost ring of cells are just migrating outward. They will not form the embryo, and then there is going to be an internal blob of cells that will form the embryo. And this basically will be, these two different distinct regions will be separated by a repeller number 1. And this you don't have to know anything about the biology of this system. This is just coming for free from the analysis. It says, oh, there is going to be a very strong compartmentalization from what's inside and what's outside. And then, even more interestingly, there is another ridge or a repeller in here, which happens to be right in the middle of this domain of attraction. Okay, so this is another ridge. So if you think, remember guys, this is the scalar field. It's high when it's orange, right? So this very high value here and very high value here. And this ridge, repeller number 2, is going to split the domain of attraction into two regions, the anterior part and the posterior part. And in fact, these cells are different. So the cells that are in the anterior part and the posterior part are different. They will form different types of, organs, etc. Right? And you can have this compartmentalization just from velocity data. No model. This is all data, okay, which is just noise and all the stuff. Okay. So again, scalar fields over initial configuration, the repellers and the domain of attraction. Scalar field over the final configuration, the attractors. Okay. Yeah.
So why is the exponent negative in the first one? It has to be positive, right?
No. This is the logarithm.
Oh, this is
the FTLE. Yeah. It's FTLE. Okay. Yeah. Okay. So it could be if it's negative, then the largest eigenvalue is less than 1.
So it's that, right?
It's basically, that means that the region is shrinking a lot. So also the largest eigenvalue is going to manifest contraction. This is in fact regions that will shrink a lot. but the ridges are still, positive. That means that there's going to be separation. Yeah, but yeah. So another thing that you can get it for free, that whenever the finite time Lyapunov exponent is less than 0, that means that this region is compressible on average. On average, because you're accumulating compressibility over 12 hours in this case. Because another interesting question that you can ask is, okay, when do they form these structures? So what I'm going to do now, instead of just using the full length of my data set, I'm going to do this analysis. I'm going to say, okay, start from here. I'm going to compute repellers over a certain time scale, which is I'm going to iterate it every, 20 minutes or 40 minutes, okay? And the attractors and the domain of attraction. And then I will just scan all my data set with this progressively increasing integration time, so that I will really learn how the shape of these features will emerge. So basically, I'm going to do it here. So at 20 minutes, in 20 minutes, the deformation rates of this velocity field, they are very low, so nothing has really deformed. Okay, so therefore, you don't really see structures. Then if I let this go, you see, for instance, the attractor is going to form. You can really see what you can also see the domain of attraction. So this is going to tell you, look, by this time, these cells, this blob of cells, they know that they will be entering the streak. It's very powerful, because you say, okay, now, what causes that to happen? Is it some genetic, programming up front? Is it some self-organizing effect of mechanics, patterning, and gene expression? This is something that you can explore just from data. And you can also look at the repellers. For instance, you see, at some point, at 300 minutes, there is the formation of, I don't know when this repeller starts to form. We can see, at 100, 360 minutes, there is this repeller that forms, that splits the anterior part and the posterior part of the raptor. Okay. By the way, the way I color these dots is I put basically green particles north of the repeller 2 within the domain of attraction, and the magenta in the south. Okay, so that you can really see what's their effect. Okay, so basically this is it. So basically you can scan your data set and learn where things form. Okay, how do they evolve, how they move, how they deform, and you can do this using velocity fields. And remember, if you would have the classical, asymptotic coherent structures, they would be fixed. They would be anchored to, a fixed point, the limit cycles, or higher order, structures. This instead, they're very dynamic.
So also, with this embryo point, so this is early stage of embryo.
Yeah, early stage.
So there's also mechanical strength difference. I remember one side, the anterior end is more solid-like compared to the posterior end. So will that also get reflected in some?
So in this system, not yet. It's not. There is not yet this. This is much later stage when somites will form. But yes, any mechanical. So eventually, our collaborators are measuring velocities. These velocities are the outcome of mechanical forces, mechanical properties, boundary condition, etc. So this is all the outcome of it. Okay, and we actually also did a few papers in which we built a model, a liquid, an active matter model that can reproduce these flows from the forces. Okay, so but this is different. So, but everything is in here. And the interesting thing is that because now, for instance, you know where these structures are forming, and you can know the spatiotemporal coordinate, you can go to the experiment, who does the experiment, and say, hey, this is forming here. Let's try to understand why. So let's do target experiments before the repeller form, after the repeller forms, and then measure, try to understand, or reverse understand what causes these features. Yeah.
The color scheme in the middle, is it density?
This is this field, backward FTLE. Okay, it's very small because in embryos separations are small. Okay, this is not really chaotic mixing, and the times are large. So when I divide by time, it's 12 hours, right? And I have separations that are of the order, I don't know, if you have a separation of, let's say, the relative strain 2, 3 maximum. So then that's why it gets to a small value. Yeah. So actually, yeah, in these systems, you can actually even not take the logarithm. Because usually you take the logarithm when you have really exponential separation, but here you can just take the largest eigenvalue of Cauchy-Green square root, because this is really going to tell you the strain, right? So it doesn't matter, it doesn't really change, because the logarithm is monotonic, the monotonic function. Okay, yeah, so basically that's basically an example, and this is what these structures can give you. Maybe in the afternoon we'll give you're going to compute those from the analytical example that we discussed in the class with Sahil and other people, and maybe a double gyro or other system. But I mean, this is basically this is how it looks, how the scalar fields will look. Another very quick example is that this, you can sort of use it as a morphometric, because for instance, if you do a knockout and you treat this system with an FGF receptor inhibitor, you see how these structures are changing. So for instance, this knockout is going to eliminate completely repeller number 2. So now think about it, this is a system that takes 12 hours to develop. So what things would you be comparing? If you just look at velocity, vorticity, which one would you look at? For over which integration time, which space? This is instead a very compressed representation of this dynamic process. And you can maybe study the length, the size of the domain of attraction, say, okay, in this system, much fewer cells will ingress. There is not going to be this anterior-posterior separation like it's in the wild type, and so on. So these are the stuff that you can basically explore with these systems. And I think I just want to, yeah.
So when you use this FGF inhibitor,
yeah,
then basically the flow will get suppressed. Cells will not be able to move around. Is that?
I mean, not really. They will still move, because you see that the reverse forms, but in a different way, in a way that basically you eliminate these repairs. So this is saying you cannot really compartmentalize anterior and posterior, for instance.
Okay.
A very strong sort of compressed prediction that you can make. Okay, yeah.
But repeller one will still exist.
Yeah, it's still here. Yeah. And now we have several other papers in which we understand, because we know the forces, we also understand why. Yeah. And actually, looking at, being guided by this compressed representation of attractors and repellers, we were able to develop the model and then discover many modular mechanisms. For instance, how does the embryo control shape change? How does it control or regulate the area over time versus the shape? Because we were saying, okay, can I knock out repeller 1 and not repeller 2 and vice versa? And just because we started with this question, we were able to implement it in the model and in the experiments. It guided us to discover some modularity of mechanisms, these types of forces. Yeah, that could be a way to use it. Okay, I'm just going to skip. I mean, of course, you can use it for, flows, like two-dimensional flows, and understand how these ridges of FTLE or repellers will form. And we can also discuss this later in the afternoon. You can also do this in 3D with sparse data, and the FTLE in 3D, and see where these ridges will separate basically tori. I mean, this FTLE field was, studied already in the past. I mean, George Haller has a paper in which he computed FTLE on this ABC flow, and this in here, the goal was more to develop a technique that is, if I have sparse tracks of cells, not dense velocity fields or analytical velocity fields, which is basically what you get when you have cell tracking, can you still compute these attractors and repellers? And this is basically what we did in this work. And we also apply this, to active nematics and etc. So you can basically use it for any system, basically. As soon as you have a velocity field or tracks of trajectories. And now recently we developed these techniques also to study flows on curved surfaces and also deforming curved surfaces. So when you have basically organ development, so there is flows of cells on deformed surfaces, then you can compute all these techniques, and you have codes available, which are basically shared with by you know, it's basically in the course catalog. There's a GitHub page in which you can basically look at all the codes available for these calculations. I think I want to stop here, and then we can continue in the afternoon during the tutorial. Okay. Just plug in the. Yeah. I'm going then to translate. Oh, we need to take that.
Do we need to join Google Meet or no? Huh?
We don't know.
Yeah, I don't have that. Yeah. Fine. Okay, so so basically, whatever Mathiya had taught us, that how you can generate like this finite time Lyapunov exponent, and you can use experimental data, and how you can try to, you know, do predictions. Now here, what I'm going to do in yesterday's tutorial, and also in the lecture, you learned how to do Lagrangian tracking and all. Now, till now, we have mainly focused on tracer particles. When I say tracer particle, it means that these particles are moving to going to move with the velocity of the fluid. But now, what happens if these are not tracers? They become heavy or lighter, right? Suppose there are bubbles in the flow, they're not going to follow flow, right? There will be some drag associated with that. Similarly, if you have heavy particles, they're also not going to follow the flow. There is going to be a drag associated with that, right? So what happens if you have those kind of setup? Also, what happens if these particles are not spherical, but they are elliptical? If they become non-spherical, how does that going to affect the dynamics? So these are about the passive nature particle. Now what one can do, one can also think about what happens to the living organisms. If you have living organism in the flow, how those organisms are going to behave. So throughout this lecture, what I will do, I will focus on these problems. So I will briefly just try to give you an overview, and what we'll try to learn from here, that even if the flow that is driving these dynamics is not known, because once you say that your particle is no more tracer, it means you do not have information of the flow. If you have particle dynamic, only the particle trajectories, it means that there is an underlying flow plus some other effect that is giving rise to these dynamics, right? So what we'll try to learn here, that we'll generate these artificial setups, okay, and then these tracks, and then using those tracks, can we predict you know, where are going to be attractors, where are going to be repellers, and once you learn, then you can also try to, you know, connect it with the experimental observation. So that's the aim of this overall talk. Okay, so let me give you briefly a few examples. For example, if you have like heavy particles, they can. This is a very typical example. If there is anyone who is doing turbulence and they are going to talk about heavy point particles, this is where they will start. So they will say that if you think about cloud formation, right? And basically when the rain is going to happen, you have to understand. So cloud is, can you tell me what is cloud made out of? It is water vapor, and only water vapor, or is it a mixture of droplets and liquid droplet and water vapor? It is a mixture, right? But usually the water droplets are of the order of micron size, right? So, sometimes sub-microns also. So if it is of that size, micron size, but when rain happens, the drop sizes are much bigger, right? Millimeter to sometimes it can be even very close to centimeters, right? So those are like much thicker droplet. And usually if you think about condensation, if there is, you know, if only condensation is driving the, you know, droplet formation, means from vapor, water vapor to liquid water, it is going to take really long time to actually, you know, droplet to form. So what happens, turbulence is the one which is in background, or the background flow which is there. Together it drives the condensation. Okay, so that is one example where if you have there is a density difference, and if there is a background flow, that can lead to so basically what will happen, there will be formation of attractive regions, and that leads to droplet formation. So suppose there are two droplets, they come and then they come closer, then they will coalesce, right? But you have to bring them closer. So there are in these clouds these attracting regions, okay, and that's what drives the faster droplet formation. Similarly, one can think about this planet formation, right? So in the early years, like we are talking about billions of years. So what happened at that time, there were dust particles, right? Now these dust particles, of course, they were heavier than the atmosphere around us, and basically what will happen, again, if there is a flow around it, it will drive these dust particles, and then these dust particles will come closer, and then they can coalesce again. If there are two dust particles, they come closer faster, they can stick. Means you can do these kind of tests, and you can see. So this is how one can try to understand planetary formation, and then of course one can also think about collective behavior in turbulent environment, right? If there are marine environment, how fish or microorganism, how do they swim together, and how do they try to find the nutrients? So all these problems one can try to. So these are the kind of examples we are going to focus, and how one can try to use the idea of inertial particle dynamics and flow and try to understand it. And again, we'll try to connect it with the pattern formation or structure formation, and how repeller and attractors can help us to understand the dynamics. Okay.
Sir,
yeah.
Talking about the reason of attractor or repellers.
Right.
So what is the cause or reason it is coming?
So once we know, then we can try to investigate. That's exactly what Matteo said, that once you know that there are reasons of repeller and attractor, then you can try. So basically the example that was considered in the earlier talk, it was about embryo. We do not have much information. What are the driving forces? What are the mechanical forces? So the information that we have in terms of tracks, everything has been integrated out. There is, of course, there is a flow. If you look at the structure, the early structure where the elongation happens, you can see that there are these counter-rotating vertices. It appears like there are counter-rotating vertices, and that leads to these elongation, right? And so there is, of course, there is a flow. Then there are other mechanical forces. The mechanical property that comes into picture, it is not a viscous fluid. It is a viscoelastic fluid. That's what we believe, and actually it has been tested, and we know that there are elastic properties that also come into picture. So you don't worry. To begin with, what are the underlying forces? First, you try to understand whether the reason of attractor or repeller exists. Once you have, then you try to dissect them and try to understand that, okay, if this is one possible reason for this, let's knock it out and see how the dynamics is going to get affected. So you break down everything, and then you try to understand the underlying forces, and then you combine, and you can also put weights to different forces, and that's the aim of all these things, right? What are the forces which are working, and how do we? So that is the question that one tries to address, but one can use this kind of approach to address them. Okay, fine. Okay, so here the idea is very simple. So basically, for example, in case of raindrops, what happens? So basically, okay, let me see. I think, and one of the next examples I have written. So basically, when you think about dust or droplets, so the same dynamics is going to happen. There will be regions of attractors, and it is going to happen in the strain-dominated region. I will show later. I will show some videos where you can see. So what will happen? These vertical regions, they will act as a centrifuge, and they will try to push heavier particle outside. Okay, you might have done it in your senior high school. So if there are heavier particles, and if there is a vortex, the heavier particle will be pushed away. Right? So that's what happens. If the particle density is greater than the fluid density, and if there is a rotation that is happening, that those particles will be pushed away from the vertical regions. And once you will be pushed away from the vertical region, where will you go? You will go in the strain dominated region. Let me draw it to explain you what I mean by this. So consider two regions. So the double gyre flow that we are going to talk about, if there are two vertices which are moving like this, counter-rotating vertices. So whatever the material you have inside, they will be pushed towards outside of these vertices, right? So where will they come? They will come closer in this region. So this is the region where the strain is very high. Okay. Now in these regions, these particles will go, and then they will start to. So if there are droplets, they will start to coalesce. If there are these dust particles, they will go, and then if there is any degree of moisture and all, they can coalesce again. Okay. So that's what happens, and that's how you describe the planet formation. That's how you describe also the raindrop formation. Okay. Similarly, you can take another example of like if you think about this phytoplankton plumes in the ocean, again the similar argument you can use. Okay, so here the idea is that compressibility also comes in. This is a 3-dimensional setup, and you can see how the patches are going to form. So let's skip this and let's go to the equation of motion. So the question is how to model these systems. This is good. Okay, so this I had already shown in the earlier case, that you have to solve, if you really want to simulate it, you have to solve Navier-Stokes equation, and then you have to look at what is going to be the dynamics. If there are tracer particles that we have seen before, that you have also tried to simulate in yesterday's lecture, you simply said that the velocity of the particle or these tracers is going to be exactly the velocity of the flow. You do the interpolation and you know exactly what it is going to be. Now if you have a scenario where, so this is the case when you have tracer particles, but now if you say that if suppose particles are heavy, okay, of course this will not be true. There is going to be an additional contribution. If you say particles are lighter, again you are going to have an additional contribution. If you say that particles have their own activity, that is also going to contribute to it. If you say that particles have some how should I put, they are not spherical, right? So if they're not spherical, again that information is also going to come into picture. So we'll try to look at, so what I will do, I will show you the equations that it will describe, and then I will show you the consequences, how the distribution is going to get affected. Okay, that's all we'll try to do.
But we consider them to be point particles.
We'll go for finite particles also. Okay, so we'll consider all the possible scenarios, but of course we'll not be very rigorous. If you want details, there are proper citations there you can go and read. Okay, but here I will give you flavor that how different shape, different degree of activity, the density difference and activity is going to affect, and also finite size. You'll see the finite size has a very beautiful effect. Okay. Oh, this we have already done. Okay. Now, let me skip this video. So this is just to show you that how the particles move around in turbulent flow, and if you wait for some time, you will see that it may go and it can get trapped in one of these vertical regions. So if you wait for some time, you will see. So by the way, this work it is an old work that was done by again Prasad from TFR Hyderabad. Okay, let's wait. Yeah, so you see it goes into one of the vertical structures. This is, by the way, tracer particle. Okay, it goes and it gets trapped, and once it gets trapped in the vertical region, it is going to stay there for some time, and the only way it can exit the vertical region only when the vortex gets destroyed. Okay, that is the only way it can get. Okay, this way. Okay, now you have already done tracer particles. Now what happens if you have a heavy particle? So simplest way to model is, you will say that heavy particle, so of course a flow will try to advect the heavy particle along with it. So it will have a contribution from flow, but then because of its weight, there will be an inertia. It will not be able to follow the flow precisely. So what it will do, the simplest way to model it, it will try to follow the flow with some lag. Okay, that is the simplest possible way. So what you will say, that there is going to be an acceleration term, and in each, so velocity, so if you look at this equation, this is the current velocity of the particle, this is the velocity of the flow at the position of the particle. Okay, so it will not be exactly same. If particle is moving with a velocity and if there is a flow in which it is moving, it will not be exactly same. And if it is not, it will not be exactly same. What will particle try to do? It will try to catch up. It will try to reach the velocity of the flow. Okay, and now how much time it is going to take, that will be defined by tau s, and this comes from this equation. Like what is the density of the, so here rho p and rho f represents the density of the particle and density of the flow. A is the particle radius, mu is the viscosity. So if the density difference is used, it means that the time scale is going to be larger. That means there is going to be a longer time scale for this catch-up. Okay, that's how it is going to be. If the density difference is weak, then we know that it will be more or less same, and again it is going to be act as a tracer particle. But if density difference is like significant, you will see what I mean by significant. You will see that then there will be a very interesting dynamics where you will have a preferential sampling. Okay, there could be another scenario where your rho p becomes too large, which means that the time scale it takes to catch up with the fluid velocity is going to be large, right? So by the way, everyone can connect it easily, right? Here the negative sign ensures that this velocity will always try to approach the fluid velocity, right? And this is the time scale that sets how much time it is going to take. Now if rho p becomes large, which means that tau s becomes large, it means it is going to take really long time. And you can also think about if there are really heavy particles in the flow, whatever you do, it is going to take its own sweet time, right? But of course, since it is in a flow, it will move around. Now in that scenario, if the correlation of the flow so of course whenever there is a flow, there is going to be a correlation time, right? If the correlation time of the flow is going to be less than this time, it means that the particle dynamics will not have any information of the flow. And in that case, you will see that again it becomes means the information is getting lost there. Okay, we'll see this example also. Now what one can do, one can define a dimensionless number for these quantities. So tau s is nothing but corresponding time scale, particle time scale, and tau eta is the flow time scale. And based on this ratio, you can say that so this using this number, you can actually say that what is the sweet region where you would like to be to understand the dynamics that we are going to focus on. Okay. Now here what I'm doing, I'm changing the Stokes time. Okay, this is again a background 2D flow, and in this case the Stokes time is very small, which means your Stokes number is small. In these regimes, your Stokes time is exactly same as the flow time scale, and then you can see the particles are now start to getting accumulated in the regions where the value is 0. So in the background I have plotted vorticity. So you can see that these particles are getting repelled from the vertical region. Exactly the same thing I was saying here in this plot. If there are these two counter rotating vertices, the particles will get out of it and then they will try to get accumulated in these regions. So you can see that when your Stokes time is small, which means that the density difference is weak, you don't feel the effect of flow. But as soon as your Stokes time becomes comparable to the flow time scale, you will see that there is a strong correlation, and the particles start to get ejected from these vertical regions and then they start to get accumulated in these regions. Now again, when your particle time scale becomes even greater than the fluid time scale, at that time the correlation, the information of the flow will not play an important role. So it will try to catch up, but by the time it reaches those the regions which are strain dominated, the flow has already changed its structure. Okay, so what you will see that they will become independent of the flow topology. What is the flow topology at current time, and what is the structure of these particles that is going to be independent of it. Okay, so this is how. So again, you can see. So this is actually a very complex problem, because you can see that these structures are very short-lived. These are not going to be long-lived because there is a strong dynamics. So background flow is moving around constantly. In the earlier example where we focused about the embryo growth, right? So there you can see the dynamics was, so everything was happening over a time scale of 12 hours, 720 minutes. But here things are happening of the order of minutes, right? Minutes or maybe tens of minutes, right? So things are pretty fast. But again, what you can do, if there is a structure, it is short-lived, you can look for those time scales and then you can try to find that, whether there are regions of attractors or not. And then you can try to do the similar analysis that has already been done. Now, what I will take, so this one is a more controlled example. So here, this is a turbulent flow. So you have seen that in turbulent flow, vertical regions are moving around. But if you have a flow where you have slightly perturbed vertical field, so here I'm plotting a parameter which is known as Okubo-Wise parameter, which is the difference between omega squared minus sigma squared, where omega squared is vorticity, sigma is strain rate tensor. So basically, it tells you that what are the reasons of high vorticity and high strain. Okay. So here you can see that all these guys are again going to be in the regions of 0 value where the vorticity is small. Okay. So here you can see that to begin with everything was homogeneous, all the particles were homogeneous, but again they go and they get attracted in the regions where the strain is high. Okay. So this is what, but
So the vorticity.
no, actually this is vorticity field. I thought it was Okugo's parameter. It is vorticity field in the background. Yeah.
Yeah, I'm saying that is that magnitude is also changing, or that those are fixed on?
No. So this is a time. So basically, in the background you have a viscoelastic flow. Okay. So you have a forcing that gives you these counter rotating and rotating vortices like double gyre flow. Okay, but then if you bring in elasticity, you can see that your structure will not be stable anymore. There will be a dynamics associated with it. Okay, so this is what you are going to get. So again, you can see that there are these patterns. You can see that these patches are appearing, right? So what I'm trying to say that even from very simple ideas, you can have different kind of patches, and one can try to address the question. One can try to use these techniques to address these questions. Okay, and again, the important thing to note is that even though the underlying flow is Navier-Stokes equation, incompressible flow, but you can see that the phase space is contracting, right? If it was a tracer particle, what would you have expected? If it was a point particle, tracer particle, what do you think would have happened? It will follow the flow, yes. And what will happen to the phase space? If it is a tracer particle, so yeah, sorry, go ahead. It will get trapped in the vertical region. So there will be more particles in the vertical region.
So the flow is incompressible.
Yes.
So then, they can't cluster if they just follow the velocity space.
Exactly, right.
So it will be uniformly distributed.
It will be uniformly distributed, right? Okay, so is the question clear? The question that I'm asking here, I'm using heavy particles. There is a time scale associated with these particles. They will not be able to follow the flow exactly. They will follow the flow with a drag, with a delayed time scale, right? But what have we set that drag to 0? Okay, that means that the acceleration is so high, that means that your particle velocity is exactly same as the fluid velocity, right? Now in that case, what will happen to this? Will you still have some degree of clustering, any preferential? So here you can see that there is a preferential clustering. Preferential because they want to stay in the regions which is low in vorticity, right? So what will happen if you have tracer particles? So basically tracer particles will not have any such preference. And as Hridaya said that, since we are talking about incompressible flow, so phase space will not contract. Phase space will be as it is. It will be homogeneously distributed. Okay, fine. So again, by the way, I have used point particles here. All the particles are point. They do not have a finite size. And again, going back to the assumption, like, if you think about dust and all, and if they are dilute, one can do this kind of approximation. Yes, Mathiya, you.
So how does that the equation for these particles? How do they differ from the? I mean, why didn't you use, for instance, the Maxi-Riley?
No, so it comes from Maxi-Riley. Okay. It comes from, but then you remove you say history term is gone, the finite size effect term is gone. So you fraction correction, all those corrections you do because you are in the limit where it is point particle mathematically, and then you say that the only difference is in the density. So this is the term that is going to contribute. Okay. Then okay, fine. Oh.
No, it goes crazy there. I think it's the pointer.
Oh my goodness.
It's trying.
Okay, now one can do all sort of analysis. You can see that since it is going to a phase space is contracting, one can look at the dimensionality, means what is going to be dimension. One can do fractal dimension and all, means all those things are there. We will not be focusing on that. Now let's see what happens if you have light particles. Light particles means the density of these particles are going to be less than the flow, and then you will have an additional contribution. Again, it comes from Maxi-Riley equation. I'm not going to describe how we are going to get it. So how your equation is going to get modified? Again, the particle will will not have exact velocity of the flow. It will always try to catch up, but then there will be an additional contribution where you will have beta into A, where A is the acceleration at the fluid acceleration at the at the position of the particle. Okay, and together these will give two different time scales, and one can say that what is the density. Means based on density difference, you can actually calculate this parameter beta and this parameter tau p. So these are the control parameters that we have. Now, if you have light particles, again using the same idea of centrifuge, what you will observe that all the particles get clustered in the vertical region. And this work was very nice work was done by Cencini in early 2000 I think 2005 2006, where he, or maybe 2008, where he showed that you can have three setup. When you have like tracer particles, all the particles are going to be homogeneously distributed. If you have heavy particles, all the particles are going to be clustered in the strain dominated region. And this is the case. So of course background flow has not been shown, but it has been quantified in a statistical sense. And in the case where the particles are light, they are going to be clustered in the vertical region. Okay, so you can see that these are attractors which are short-lived, and the life of these attractors are going to be the lifetime of these vertical and strain dominated region. Okay. Okay. Now let's jump to the living organisms. So there was this famous experiment done by the group of phi is the swimming number. By swimming number, what we mean that what is the activity of these agents. So basically, if there is a swimmer, it will have its inherent velocity, right? And of course, if it is going to move in a flow is going to have a characteristic velocity. The ratio of these two, how fast you are swimming compared to how fast flow is moving, is going to give you the swimming number. So there are two control parameters in this setup. Okay. Now here in the experiment, so of course in experiment it is much more challenging to control like swimming number, right? Means we know that if it is a motile organism, it will have motility. And the other extreme case that you kill them, so they will not be motile, right? So that's what you do. So that's what actually they did. Okay, they had motile particles, means motile swimmers, and then they had dead swimmers. Okay, and then you put them in this this kind of flow, double jet flow. Okay, and what they realized that when particles have motility, they have this strong clustering. So this is the density map. Okay, you can see that they start to get clustered in these regions or these regions. Okay, and this is from experiment and this is from simulation. Okay. Okay, so this is the observation. So you can see that activity plays an important role. So if you treat them as a tracer particle, you will see that they will be homogeneously distributed. But as soon as you bring in motility, you can see how nicely the distribution is going to be. Okay? Yeah.
What about the density of this particle here? The density of this
more or less same. But there is no density mismatch. Okay? Yeah. Any other question from the setup? So you can see that there are certain particles which are in the vertical region. The reason why they stay in the vertical region, so if you initialize anything, it takes time to get ejected from the vertical region, right? And the time scale it takes to get ejected from the vertical region is going to be controlled by what is your swimming number. If you can swim faster than the velocity scales of these vorticity, then you can exit it faster. Otherwise, what you will do, slowly you will try to go against the stream, and then you will cross the streamline step by step. So you have like, if you're somewhere here, flow will try to rotate you, and if you're swimming, you will try to go like this. Slowly you will move. If you can swim faster, you can exit this region, and as soon as you exit, you immediately get trapped in these hyperbolic regions. Okay, these are hyperbolic regions. Okay, strain dominated regions.
What is the stability number?
So stability number. So Yeah. So psi is point. So they have used different stability
But
number.
what's so swimming number is the speed of the.
Oh, okay. So stability number, the definition.
Yeah.
Okay. So the definition is. I need to check. I think. So B is a tumbling. How fast you are going to tumble. So basically, these are gyrotactic particles. So basically, they will try to climb up in z direction, but after some time they tumble. Okay, so there is a tumbling frequency for that.
Yeah.
And then the other one, I think it comes from the vorticity, the RMS value of vorticity of the flow.
Okay.
So that's the stability number. So there are two time scale, one that comes from the flow and the other one that comes from the inherent nature of the these particles, and that is going to give you stability number. Okay, so when so this is the exact setup. This is a homogeneous isotropic simulation where you consider a 3D box and then you see how the structure is going to be. When these cells are bacteria or phytoplanktons are non-motile, you will see that they are homogeneously distributed. But as soon as you bring in motility and you control the stability number, you can see that the structures start to form. So they are again coherent structures, or high density regions start to form. Okay, fine. So this is this is what the setup is. Okay, and of course this is the equation of motion. Here P is representing the orientation vector, and this is very much similar to what you will see like a Jeffrey equation, where K is representing the preferred direction in which the swimmers are trying to go. Okay, now let's see what happens when you have. So by the way, in the simulation that we have seen before, again point particles have been considered. Okay, those are not finite size particles. Now what happens if you have active Brownian point particles and if they are moving in an imposed flow? Okay, so you will have an equation where your velocity of the particle is nothing but background flow, and then V0 into whatever the preferred direction, in which direction these agents are trying to move. Okay, and then you will have, if you are a non-spherical particle, right, what will happen? You will have a dynamic. So this is Jeffrey equation, your famous Jeffrey equation, where omega is vorticity, alpha is the aspect ratio, means how far you are from your alpha is a parameter that comes from gamma, and it tells you that how far you are from isotropic state. So if gamma is large, you can see that alpha is going to be large. If gamma is 1, alpha is 0, which means that you are spherical, you are isotropic in nature. So of course when gamma is 1, which means alpha is 0, this term disappears. For a spherical particle, there is not going to be any contribution from this, but as soon as alpha becomes finite, you are going to have a contribution which is going to be something like this, where n is again orientation vector in which these particles are going to move, so in this case it is going to be the natural direction. So these particles are like deformed particles, so they are no more sphere, they are going to be something like this. Okay, and this vector is your n vector. Okay, now E is strain rate here, and together with that you are going to have a dynamics. Now if you have a homogeneous, so if you take these kind of particles and if you put them in a a roll mill flow, okay, so you have like these are like negative, these are counter rotating vortices, positive and negative vorticity value at the core. What you will see that if you don't have any non-sphericity, if these are only active, they are going to just behave like this, means they are going to be homogeneously distributed. Okay, if they are non-interacting, but non-interacting, which means they do not have any size, and also and they do not have any size. Let me quickly go through this. Okay, so in the earlier examples, what I had shown you the distribution, how the particles are going to be. Okay, now if you say that there is also non-sphericity that comes into picture, now this becomes interesting. Here what I'm showing you the results when alpha is 1. Alpha is 1 correspond to a high non-spherical value, and V is nothing but the ratio of the swimming velocity compared to the flow velocity. Okay, now if you are in a non-spherical particle, which means alpha is equal to 1 correspond to actually rod condition, right? Means you are completely elongated thing. If you are rod-like particle and if you have a swimming number which is of the order of this, you will see that you will go and you will get clustered in this strain dominated region, right? Again, all these calculations have been done for the point particle. They do not have any finite size. And as soon as you start to increase the, so here you can see that V is 0.016. If you increase your value of or activity of these agents, if you approach a value 0.095, what you see that it is no more this sharp, right? You can see that here it's very sharp, means very fine clustered region. But as soon as you increase your velocity, swimming number, let's say, you see that it starts to become wider and wider. So can you tell me why that should be the case? Or can you tell me why there should be a clustering? Any idea, any intuition for this? So now the setup is you have active Brownian particles. So in vertical region they are always rotating, right? So there is so and the strain dominated regions, since there are just vorticity is weak, right? So they will just be moving in this straight line. Okay, so that's how it is going to be. Now, but the question is what you expect. So if you set velocity equal to 0, so in the earlier, if you say that my velocity is 0, right? Then what do you think, what do you expect is going to happen? You say that activity is 0 and you have non-spherical particles. Then what do you think, what is going to be the distribution?
Non-spherical or spherical?
Non-spherical.
Trying to align with the flow.
Yes.
Major axis.
No, that is fine, but I'm talking about the distribution, the density distribution.
Uniform.
Uniform, yes. It doesn't matter. It will be aligned, but it will be homogeneous.
Homogeneous, right? It will always be homogeneous. So it doesn't matter how it is aligned, but here what we are focusing on the density distribution, right? So you'll see that your density distribution is again going to be uniform, but as soon as if any small value of activity you introduce, so it is like a singular value, like any positive velocity will kick in and it will move them to these regions. Okay, but the interesting thing is that if you start increasing your velocity, this activity value, okay, then you will see that these regions will not be sharp, and the reason being because of this activity that it can go out of those regions or those stable regions. Okay. Okay, fine. Again, you can play with this aspect ratio and these velocity values, and then you will.
The second question, should there be a dot at the time?
There is a dot. Sorry. So this is Ni dot is there. So okay. Okay. This is standard Jeffrey equation. I think there should be so there is this is Ri dot and this is Ni dot. This is the dynamics of how the orientation vector is going to be.
First term is active Brownian.
Yeah, this is ABP, active Brownian particle, and the second term is Jeffrey equation. So that comes into picture only when you have non-sphericity in nature.
Omega is given.
Omega is the flow, background flow. So it is moving in this imposed flow. Vorticity. Omega is vorticity, E is the strain rate. Okay, strain rate tensor.
And it doesn't have this DR rotational.
No, means in this case, in this setup, because once you bring in rotational diffusion, that adds up another complexity. But what one can do, so if you recall your standard active Brownian particles, what you will have an additional diffusion, translational diffusion term, right? But what we are doing to make life simpler, we are saying that let's kill the translational noise and then do the analysis here. But of course, you can bring in your translational noise and you can see how things are going to be. Okay.
You see that the asymmetric particles,
yes.
For if they're down, if there is no activity, they're homogeneous.
Right.
Why?
So basically, what you have to do del dot u equal to, you have to set what is going to be the value of del means divergence of velocity field. So if you set this things, so the thing is that we are setting activity to 0, right? So this term disappears. So they become tracer immediately.
Oh, okay, so there is no inertia.
No, so we are so they are non-spherical, but activity is 0, right? That's the question, right?
Okay.
So once you remove activity, so particle velocity has two contributions. One contribution that comes from the flow. So whenever I write u, that represents the flow velocity, and u in the bracket Ri means flow velocity at the position of the particle. Ri is the position of the particle. And V0 Ni hat represents the velocity due to the active nature of the particle. So V0 is your self-propulsion speed, and Ni is the direction in which you would like to move. And that Ni comes from means the non-spherical, means in whether you are like this or what is this vector N hat. Okay. So as soon as you say that my activity goes to 0, this term disappears. Now if you take a divergence of u, this is tracer, means exactly the same argument what you have for tracer, it is going to work for this, and it is going to be homogeneously.
There is some drag effect.
No, so that we are not taking into account. So of course you can make, so with time we'll make it more complex. So we'll also bring in inertia. So you will see that what happens if you bring in inertia. Okay. Okay. Any question here from this part? So by the way, this is the example that you have to do in the afternoon. Okay. So what you will do to begin with, you will start from tracer particles. You will put them in this roll mill flow. This flow you have already done, right, yesterday. You have also evolved tracer, right? Now you will use that information, and then you will try to compute what is going to be FTLE value, and then you will try to see that what are the reasons where eigenvalues are what is the profile of maximum eigenvalue, right? And from there you will try to estimate. Now what you will do, so for tracer particles, all good, everything is fine. But once you bring in this information, then you have to look at the tracks of the particle, and based on the tracks of the particle, you have to estimate what is going to be your eigenvalue. So that is going to be slightly tricky to handle. Okay. So the task will be, you take the flow that you already have, you evolve the particle using this equation. Of course, there will be tutors, they will help you how to do that, and then you have to, calculate what is going to be finite time Lyapunov exponent. So for these guys, these reasons are acting as an attractor, right? So that's what you have to identify using FTLE. Okay. Similarly, when you have heavy particles, there also we have seen that these reasons are acting as an attractor, right? So today you will try to do two examples. You will have elliptical particles in roll mill flow, and these reasons are attractor. You have to use FTLE, and then you have to show that yes, they are actually, even FTLE is showing that they are attractors, right? Similarly, you have to do it for the heavy particles. Okay. So these two examples you have to do today.
How should I understand this aspect ratio and their point?
Aspect ratio and then?
When they are point.
Okay, so you're saying that if it is a point particle, what is the meaning of aspect ratio? So in reality, there is nothing like point particle. But what we are saying that there will not be, so we are always talking about limiting case. Okay, so the way in the context we are saying that they are point particle, we are saying that they will not be able to, so they are so small that they will not be able to interact with. So again, we are always considering a dilute suspension. Okay, and then we are saying that they are so small and so dilute suspension that they will never be able to see each other. Okay, and then they are not going to affect the flow that is happening around them. They are so small. So in that spirit, they are point particles. So basically, there will not be any interaction among them, and then they are not going to affect flow. Then in that spirit, you can always consider that they are going to be point particle. Okay. So whenever I say point particle, that's what we mean. Okay. So the simplest reason why you want to deal with point particle, because it is a lot easier. First of all, it will not affect the flow. Incorporating the fact that the point particles are finite, they themselves will start to modify your flow, right? So that becomes another complex problem. And then if particles can see each other, then they will have their own interaction, and that will also come in the equation of Ri dot, and we'll see in few minutes how it is going to affect. Okay.
Maybe a comment on this is that the elongation you can think of, think about a very small spindle that you put in the water. This guy, if it's circular, it's very small, as I was saying, if it's circular, it's just going to be transported, and it's just going to rotate by the vorticity. That's when alpha is equal to 0. But when you start having a little ellipsoid, this guy is also going to feel the shear of the flow.
Right.
So it's going to rotate, not like the vorticity, but the vorticity plus the strain.
Plus the strain, yeah.
That kind of term there. That's, I think, the...
Yeah, that's...
Yeah, okay.
So non-sphericity comes only in the rotational, means how the n vector is going to get modified. That's how it comes. Okay. Fine. Okay. So now what happens if you have finite size? Okay. So if you have active Brownian particle, and once you bring in finite size, so this is without flow. If you don't have any flow, you have active Brownian particles. What you are going to have? You are going to have an equation where you have forget about this URI, that is going to be 0, because we are in the limit where your background flow is 0. You will have V0 multiplied by orientation vector, and then you will have, since there is a finite size, there will be particle-particle interaction. So particles can see each other, and then there is going to be Fij. Okay, that is going to be U Fij, and then there is this eta I term. Okay, that is the means translational noise that I was talking about. Then there is a dynamics for the orientation vector, and that is going to be nothing but cos theta I sin theta I. Okay, and this theta I dot is nothing but there is a noise term. Okay, you all, I'm pretty sure majority of you might have seen it earlier, and this is the equation which people use to understand motility-induced phase separation. So basically, if you take, if you solve this set of equation, and if you are in the limit where your packing fraction or the number density is large, which is greater than 0.4, 0.5, and if your rotational diffusion or let's say persistence time is large, then what you will see that these guys will start to form clusters. Okay, this interaction Fij is purely repulsive in nature. So basically the way it works, when two particles come in contact, they will see each other, they will repel each other, and that's how it is. So there is no attractive term here in force. Okay, these are hard sphere. Okay, so these are hard sphere, but still you can see that they start to form clusters. That is counterintuitive, right? It means why will you form a cluster? Only if you have attractive rhythm. So that's why, since they phase separate, and even though they are purely repulsive, that's why people call it motility-induced phase separation MIPS regime. This is exactly what in the earlier lecture one student was asking. So if you have motility-induced phase separation, you are going to have these kind of regimes. Can FTLE predict it? Can it predict earlier? So first of all, where you are going to form these phase separate states, we don't know. Right, in space, so this happens spontaneously. In space, you cannot predict it. But can you predict, if you have these data, can you predict earlier that where it is going to form? Okay, so
one question in that regard. So is it possible for dry system? No.
Dry system
I mean, if you don't have any background flow or anything, so in that case, will you be able to predict anything with this FTLE or?
Yes, exactly. Exactly, that's the thing. It does not matter if you are moving. There should be some force that is driving it, and if you are going to form a cluster, so in some phase space you are being attracted, right? Maybe Mathiya can. So
yeah, I mean, it really depends on these terms that you have there. I mean, so eta I assume is small.
Yeah, translational noise is small. Yeah.
So then you still have a drift, which is V0 and I plus mu Fij.
Right.
So in other words, you solve this system, you're gonna get the position of R, and then that's basically your dynamical system now.
Right.
And then you can see if there is gonna be some attractions and repellers. I suspect there is. If there is, if you start seeing these objects that through this, I mean. You know, maybe you should guys compute it in the afternoon, because I mean, once you have the code,
they'll go crazy. All this
changing the velocity is very simple, right? So
yeah, it can be done, and the codes are available, easily available. It is not very challenging. So one can. So this is also one can do, and I'm not sure. I'm actually quite confident that it has not been explored from this point of view. Okay, so whatever examples I have shown till now, it has not been explored from FTLE point of view. Okay, so one can try to use these ideas and try to implement and check it for the first time, that whether it is making sense or not, and whether you can actually predict these things or not. So we can see, you can definitely see that things are being attracted, but whether FTLE is also predicting the same thing or not, and what more can be learned from it. Okay.
So this is but without a background.
Yeah, this is without a background.
MIPS is without a background.
MIPS, yes, it is without a background.
That is very counterintuitive.
Sorry?
That is very counterintuitive.
So that was the question. That's what Anupriya was asking. And that's what Mathiya is saying, that, you know, if you have a dynamics, it is a dynamical system. Like when you did the calculation, when you said x dot equal to minus y and y dot equal to x minus, or I'm changing the minus y. Sorry.
What is the dynamical?
Yeah, what was the
right? But still.
Still you can compute, right, where are going to be attacked. So exactly the same way. So here you can say that these are particles, they're moving with this force. Then you can say that let's get rid of it. Let's say there is a flow field and that is driving. These are nothing but tracer, but there is so what you have to find, an effective flow field that is driving. What is so phase flow, exactly the flow map, right, that you have to find. Okay, flow map does not say that there should be actual fluid flow. Okay, So that is very important that you need to understand. That's the reason I'm giving these weird examples to you so that you can connect. Okay, fine. So we can do it. If there is flow or no flow, it doesn't matter. Okay, it is it. Sorry.
Yeah, I mean background flow is under any flow. It has to have some flow on its own, like
yeah, means if there is a dynamics, you can say that it is moving with some flow, some route.
What I was confused about was FTL, I understand we can calculate, but if there is no background flow, then why would these particles question at all?
Oh, you're talking about this example, yeah. Or any example. So yeah, so we don't know what. So for this we understand very well what happens here. Okay.
So the only forces are repulsion between the particles,
right?
And active.
They have activity.
And just then they form clusters.
Right, but you have to have certain. So there is a threshold value for the activity. Also means actually the ratio. So there will be two time scales that one can get, but the packing fraction also plays an important role. So if you are very dilute, you will not be able to see these clusters. Okay, so that's why if you're dilute,
you're basically asking what is MIPS. Yeah.
Okay, that we can discuss. But that's what MIPS is. Okay. But then what one can do, one can take these active Brownian particles and put them in a background flow, again Rollman flow. Okay, and what you will see that based on what is the swimming number, so it is exactly V0 is the activity of these guys, and V eta is a characteristic flow. So here it is Kolmogorov like velocity. What you will see that if the swimming number is very small, then you will have a mixed state. Okay, so what happens if your velocity is weak, right? So basically flow will drive your dynamics, right? And of course the flow will try to mix things. So you can see that there is some degree of clustering in these vertical regions. But
compute the V eta form?
V eta is a Kolmogorov length scale. So basically, for this system you don't worry. But what one can do if you are dealing with a three-dimensional Navier-Stokes equation, there is a energy dissipation rate that is involved, and you consider that it is constant. So using energy dissipation rate and viscosity, so energy dissipation rate gives you a length scale and time scale, and viscosity also gives you a length scale and time scale, which have different dimensionality, and then using that you can extract a velocity, a time scale, and a length scale. So Kolmogorov length scale is nothing but the length scale where your Reynolds number goes to 1. That's the idea.
Okay. So how do I interpret it if I look at the flow, like these vortices? What is it?
No, okay.
Turnover or what is it?
So here, okay. So this V eta is nothing but the velocity of the particle. So here V eta is the largest velocity scale in the system. So basically you define U0 sine x sine y kind of thing, right? For this kind of flow. So let's say this is U0 of the system. So what is so V eta is nothing but a characteristic velocity scale. Since V eta is a characteristic scale everyone uses for the turbulent flow, that's why just to be consistent with that we have used the notation, but it is nothing but the characteristic velocity of the background flow. Now if swimming number is small, which means that the particles are moving with swimming with a very small speed, then what will happen, you will have a relatively mixed state. As soon as you start to, I think these are movies. Okay, so what you will see that again when your swimming number becomes comparable to the flow velocity, you will start to see that these guys again they start to cluster in these regimes, and if it is too large, it doesn't care about the flow, they will just show MIPS. So this is MIPS. This is the case where you will have a phase separation due to the background flow, and this is the case where you will have mixed state. So again you can see that this is it. So MIPS we have discussed, right? Then if you have background flow and where you have competing velocity, you can see that there are going to be patterns. Okay, and this comes purely because of the fact that you have a finite size. If you remove the finite size, this disappears immediately. Okay.
This is exactly the thing, like it is avoiding the
vertical regions, right? But the origin is very different. So that's why I'm saying that it does not matter what is the origin. You look at the tracks. First, you try to understand that whether there are attractors or not. You can also see the time scales. So even though the flow can be different, but what kind of particles you have, the time takes to reach those regions are going. So you can see the difference will be in the time scales and other such things. Okay. Okay. Fine. Now, so we had discussed Vichek model. I had also shown what I had given few examples. So basically, what happens here? If you're moving around, you will see your neighbor, and then you will try to align yourself with your neighbors, and then you will just flock, right? We have discussed it in detail. Now, what happens if you are in a background flow, okay, or if you are in a marine environment or turbulent flow? So again, you will see that there are going to be interesting. So the question that one can ask is there going to be a flocking even if you're in a turbulent regime? Okay, and what we'll try to do, we'll try to consider a very complex setup so that we can make it as general as possible, and then we'll try to understand whether flocking can happen or not. And again, the question is, flocking can be seen as a pattern that is emerging, right? And can one use the methods that we have learned to predict anything like that? Okay, fine. So I will skip all these things. And of course, it is not like for the first time it has been explored. There has been many work where what you do, you consider a fixed flow. Like in one case, we had considered like roll mill, which we have used quite commonly. But one can use any kind of flow, any background flow. You consider a steady state, steady flow, and there is no dynamics, and you try to see what happens if you have particles which are like Vichek kind of particle. Okay, one can do it in 2D, one can also do it in 3D. So let me jump directly to the equation of motion once, just to give you an idea what is the meaning of it. Now, what one can consider that these particles, there could be a density difference. So one possibility is that they are tracer. Other possibility is that there could be a density mismatch between the swimmer and the flow itself. The other possibility is that they can be active in nature, right? So if you are active in nature, you are going to have an additional contribution that is going to be V0 eta item. And now what is going to be the information about orientation? That comes from the fact that if you are a non-spherical particle, this is how you're going to be your direction. Okay, these two you have already seen in one of the examples that you will be doing today also. Okay, on top of that, the additional information we are saying that these particles can be inertial. There could be density mismatch, and then we are saying that since we want to model a fish school or microorganism, we are also going to add the information that they can see each other and then they can try to reorient themselves. Okay, and that means that there is going to be a Vichek alignment thing. Okay, now if you use all this information, how your flocking is going to get affected. So what we find is that so on the x-axis, the Stokes number is being plotted. Stokes number is nothing but time scale of the particle, the lag time divided by the flow time scale. If lag time is large, it means that if it is comparable to the flow, it means you are in the regime where you will be pushed in the strain dominated region. Remember, for the heavy particles, right? If the time scale, lag time scale is of the order of the flow time scale, it means you will be pushed in these strain dominated region, right? You will be pushed away from the vertical region. So, and then on the y-axis, we are plotting the alpha value, which takes into account how non-spherical you are. If alpha is equal to 1, it means that you are rod-like particle. So the range is going from some small value to 1, or both of them are on log scale. So what you will notice that if your radius of interaction is small, let's say 0.03. By the way, all these simulations have been done on a 2 pi cube box. So these numbers will give you an idea. So if it is of the order of 0.03 and there is no swimming, they don't have any, they are passive particles. So if they are a passive particle, what do you think, what is going to happen to, so if the particles are passive, do you think Vichek interaction will act or no? So by here I'm setting V equal to 0, swimming velocity is 0. So they are not passive in that spirit. Okay. So do you think Vichek interaction will have any effect if you set V equal to 0 for this setup?
Can you go to the equation once I got that?
Yeah, sure. So the equations you have, so equations are a little complicated. I will just go through them again. You take into account heavy particle information. You say that particles are heavy. So these are intermediate velocity steps, okay? So you will say that there is going to be a contribution, that is, there is going to be an acceleration. Using that acceleration, you compute what is going to be your V star, Okay, once you have V star, you say that I'm going to calculate another intermediate step velocity, and that velocity is going to be V star equal to V0 plus n hat. Okay, this is, you take into account activity. Once you have V star hat, you take an averaging. There should be a star is missing here. So you take this V double star hat and then you do averaging of that. Okay, so particle, if you are a particle, you will have one contribution, like, so first you will say that there is a density mismatch. I will have a contribution, there will acceleration, you will have a velocity from there. Once I have velocity, on top of that I will add activity, so it will move in a certain direction. Let's say this is how I'm elongated, so I will try to move in this direction, and then on top of that you will see your neighbors in a radius of interaction r end, and then you will say that I will try to align myself. So there are three different forces working on it. Okay, and I have, what I am trying to do here, since it is complex, so I have broken it down into three parts. So you will calculate two intermediate velocity, and from that you will get the final velocity that you are interested in. Okay, so first there is information that comes from the heavy inertial particle nature, second that comes due to activity, and third is the alignment. Now the question is, when you set V0 equal to 0, which means swimming number is 0, well, Vichek will be active or no?
Is it that by a star or double star?
It is with double star. It is always with double star. Sorry, there is a typo. Sorry. So since you can see, it is always going to be active, right? So it doesn't matter whether the particles themselves can move around or not. You can be advected, right? You can be advected by the fluid. That's what is happening here. So you are being advected, and since you are being advected, then you will see your neighbors and then you will try to realign yourself. So you don't have energy to move, translate, but you can reorient yourself. That's the idea. Okay, so you are dead for translation, not for rotation. That's the idea. Okay, so yeah, so that's why you see here that when you are rod-like particle and when your Stokes is high enough, which means that there will be a preferential clustering in the strain dominated region, you can see that there is going to be some degree of flocking. Okay, as soon as you increase your your interaction radius, and also you say that now I'm going to increase my self propulsion speed, you can see that the flocking region starts to become stronger and stronger. And if you make your velocity even stronger, you say that I'm going to be swim faster than the characteristic flow speed, you will see that flocking appears everywhere. Okay, that means that you can dominate the flow that in which you are moving around. So if that you can do, then Vichek immediately dominates, and this R is a kind of a decent interaction strength, so that you can see your neighbors and you can realign. So that's why you see that in most of the regions there is alignment, except this region. This is a region where your Stokes number is weak, and this is a region where you are not elongated but you are flat. Okay, you are like a disc. Okay, so if that is the scenario, then you will not see flocking. And the reason why that is the case, if Stokes, so now what one needs to understand that how Stokes and non-sphericity or elongation is going to affect your dynamics. So basically, when you are elongated, then it is easier to align. Okay, means there is a flow character, means you are going to align with the largest eigenvalue of the flow of the strain rate tensor. Okay, and the second thing is that Stokes number. Okay, if you are at a Stokes number which is close to 1, which means the flow, the lag time and the flow characteristic flow time are comparable, in that limit you will be pushed to the strain dominated region. Okay, which means your local density will go up. Once your local density will go up, then what you will see, you will have more people to align with, and that's how your flocking goes up. Okay, so that's the reason, like in this region, when you're means you are more rod-like, and when you are like intermediate to moderate Stokes number, you can see there is flocking. But as soon as you become flat, and as soon as you become at low Stokes number, you can see that it starts to disappear. Okay, now this is the representation, so you can see that, so basically Stokes number can also be connected with size, because there is an expression that comes as a squared, right? So if you are small and if you are like disk, definitely you are not going to show flocking. if you are large and if you are like this, then there are some possibility. Again, if you are small and you are rod-like, then also there is possibility. But if you are rod-like and you are large, definitely there is going to be an alignment. Okay, even in the marine environment. So that's the overall picture. That's the gist. Okay.
So basically, like how much they are interacting. The interaction range, if it is increasing, then we will see more.
So here I'm saying that interaction range is same. Our interaction is same. Okay. And so here I'm saying that I'm fixing my R interaction. I'm fixing my swimming number. Now how the shape and how the size is going to dominate. Here size can also be directly connected with the Stokes number. Okay.
Some vertical green lines also.
Where I think that is a plotting thing. That is a resolution issue. It's not there.
What is this color bar exactly?
Oh, so color bar is order parameter. So order parameter, you know, in which case you can define what is a global order parameter, and that gives you. Okay, it is order parameter. So order parameter represents whether there is flocking or not. Okay. Okay. So I have more content, but I think this is enough for you to be motivated and focus on FTLAs. Okay, and these are still open problems which one can try to address. And you can see the time scales here are very different. In one of the examples which Matthias showed, the time scale was 12 hours. And the time scales are going to be much shorter. And then we have also looked at the time scales which can be of the order of our own lifetime. Like if you think about Jupiter red spot, the lifetime is like means maybe few hundred years, right? And if you think about the polar vortex, so you can see that there are different time scales, different system size, and things are not straightforward. Okay.
So
Yeah.
can I say, or can I convince myself that suppose now I am not looking any attractor or repeller kind of things, in future I might see that because the time scale is so slow. Can I understand?
It depends on the system. So that's what was drawn here in this plot, right? What does this explain you? This tells you that you may not see the attractors immediately. You might have to wait. And that's exactly what Matteo was saying in the earlier lecture.
So basically there are, it's actually a very good point because, for instance, in embryos, so embryos develop depending on temperature. So somehow, if you basically lower the temperature, it's like reducing, in some cases, the developmental speed of an embryo. So it's like, you move, I go from here to there, and I go at the normal pace, but then I can go very slow. So if you track me for, I don't know, 5 seconds, in one case I arrive to the door, and in another case I did only one step. And therefore, this also can cause the emergence or suppression of attractors, repellents, etc. So yeah, it's a very good point. Yeah. So it may be that if you observe the system for longer, you're gonna see an attractor.
But the time scale is not only the reason, right? There could be other. For example,
there could be other things. Yeah.
So time scale.
Yeah, there could be. Yeah.
So time scale only tells you when you are going to observe the structure. That's the question. Like, what are the time scales over which you are going to observe the structure?
I have one more question. Can we intuitively understand for the system what will be the time scale by which we are going to?
Which is 1 over the FTLA. So that's gonna tell you how long should I wait so that I start seeing appreciable deformation and therefore attractors and repellers. Yeah, so that's maybe the way to start. Yeah.
It's already 1:30, so we'll meet at 2:45, okay, in the computer. Okay, thank you everyone. Thank you.
You want to continue with this thread?
No.
Okay.
Yes.
I just want to go through what other things are.
Right. I can share it with. So these are like Anupriya's work that I could not show. I wanted to show some of those elastomers and all that you had done long back just to see that